Hi everyone. We will begin in a few minutes, just for waiting for people to join the stream. And it's a new month. It's August the 1st. Can't believe 2022 is already the two-third. It's a two-third of the 2026 is over. Hi Vernon. Thank you very much for joining the stream. Yeah, and let's not lament the passage of time. Let's celebrate the beginning of August with a fantastic subject, partial differential equations. So, yeah, this is an extremely exciting topic. Hi there. And in fact, if you're an applied mathematician, the best way, perhaps, if you're an applied mathematician, perhaps the highest, perhaps the subject that will earn you a Fields Medal with the highest probability is PDE. Okay, I don't know. I mean, I don't want to sound salty at all, but I find, of course, these medals are very valuable. They inspire others to do mathematics, but we do need to bear in mind that there is a bias when it comes to the topic that it selects, the thing that they prioritize, that kind of stuff. Usually speaking, places, awards like Fields Medal prioritizes abstraction, and more, perhaps with the only exception being problems related to theoretical physics, which, of course, has a lot to do with PD. So that's why I was saying, if you're an applied mathematician, the subject that will give you the highest probability to earn a Fields Medal is probably PDE. Let's say, but if you're working, say, optimization, working numerical methods, mathematical modeling, well, Fields Medal is probably not going to be not for you. But don't worry, there are other awards out there. Applied mathematics has its own awards, and so this is the way it is. So the idea is we honor the work of the individuals who made contributions in whichever field of mathematics, but we do not. There's no need to worship them, and earning a medal don't always correlate to the value of your work. Heck, Kolmogorov axiomatized probability, right? Yeah, Kolmogorov axiomatized probability, one of the main star of this channel. He did not got a Fields Medal for that. Okay, it's such a foundational work. I mean, I don't think you will ever get a. I haven't seen a probabilist earning a Fields Medal like ever. Like, what's the logic in that? I don't get it. I mean, this is not a criticism. It's just that mathematical taste is subjective, even though mathematical truths aren't. Okay, so do not let worldly status dictate the value of your work. What about macroeconomic modeling? Well, that's more about economics rather than with mathematics. Of course, there's a lot of overlap between them, like John Nash. John Nash was a mathematician who won the Nobel Prize in economics. Anyway, so back to the main subject, PDE. So why don't we begin today's stream with a bunch of book reviews, okay? Because I know I'll probably answer these questions again, but I just want to give my recommendation list right at the start. And in particular, today we're not actually going to follow a particular book, but rather I will just follow my own notes from my own university study, because I actually prefer it over most of the books on the market. But that's not saying that the books aren't great on the subject. In fact, many great textbooks on the subject exist at various levels, beginner, intermediate, and advanced. So I would like to start with a book recommendation from I'll recommend 5 books, okay, which are really 4 books. The first one is called Applied Partial Differential Equations with Fourier Series and Boundary Value Problems, and by Richard Haberman. So this one is an introductory text and is very user-friendly. The only prerequisites for this book is a good knowledge in multivariable calculus. So you should be able to calculate partial derivatives, gradient, divergence. Multivariable calculus, including vector calculus. Okay, those things pretty well, as well as some basic knowledge. You don't need to have advanced knowledge, but basic knowledge in ordinary differential equations. Things like how do you integrate an ordinary differential equation using the method of separation of variables. How do you solve a linear ordinary differential equation with constant coefficients, right? Like the ODE for the harmonic oscillator. You should be able to do that. And after that, you're good to go. Whichever ODE that is needed in the course of study of PDEs, which actually there's a lot. PDE is actually one of the greatest impetus when it comes to research in ODE, in particular the class of called boundary value problems. You don't need to understand boundary value problems in advance to read this book, but this is the book is largely self-contained. You just need to have basically a good knowledge in calculus to start with it. Okay, so it's very applied, and it has it's in the title. Okay, it's not like some applied books that put applied in the title, but most of the book is theory crafting, and you end up perhaps one or two applications at the end of the book, as if it's some kind of afterthought. No, it's not like that. This book is very applied. Modeling, computation, and derivations, not a whole lot of proof for reason we'll explain, are very much connected. So it's a full cycle of doing applied mathematics, which is very cool. You start with a real world situation, you do modeling, and then you solve the mathematical problem, and then you come back to the real world and interpret your results. Awesome. So this is strongly recommended for beginners. This one, and if you wish to take a look at a more advanced textbook, I would recommend Evans partial differential equation, like this one, the blue, sorry, where's that? Yeah, the blue and yellow cover. This one is a classic graduate text. That being said, it says here, L.C. Evans, then this person right here, we actually did a live on his notes on optimal control just a few weeks ago, and I think I will do a wrap up for that. I mean, not wrap up the subject, that's impossible, just wrap up where we left for the last stream, in the last optimal control stream, because right now I have accumulated a bunch of loose ends in the past stream. Information theory, optimal control, finance. At least I wish to finish what I was talking about in those streams. So yeah, that's the plan anyway. But yeah, Evans is a world-renowned expert on PDE, and this book, Partial Differential Equation, is probably the most comprehensive textbook that you are gonna get on the market, because PDE is so huge. This book has well over 700 pages, and it covers classical solutions, modern techniques, linear and nonlinear PDEs, etc. And the thing is, yeah, it is a whole grad book series of those blue yellow covers. Exactly, yeah, you're completely right. But this is perhaps one of the best known ones in the series, PDE by Evans. It's a standard in grad school. I mean, we used it in grad school. But yeah, I was saying, PDE is so huge. Like the subject matter is unbelievably huge. Even though you can have, let's say, you can have two researchers in the field of PDE, and if they work on different types of PDE, the techniques can be very different. Let's say one guy works in fluid mechanics, and the PDE is in fluid mechanics, and another guy worked in, say, the PDE, say, elliptic PDE. The techniques they use are rarely transferable. Of course, some of the fundamentals are transferable, which will come come to that in a second. The field is so huge that it is virtually impossible. I'll bet $1 million on that, and that you will never see a unifying series of PDE. It's just so hopeless. Okay, PDEs come from so many diverse areas: mathematical physics, differential geometry, control theory, and also probability, etc. So this is such a massive field. You can spend your entire life on it and only will understand a small portion of it. Maybe I said this a few times earlier. Like, I think on an existential level, personal existential level, the experience of learning mathematics is a humbling one. You study mathematics and you realize just how short your life is. It's like this kind of feeling. I mean, I live in Canada, so the closest thing I can think of is Niagara Falls. You know, when I study a subject like PD, it's as if I'm standing right next to Niagara Falls. You see this unstoppable force of nature, so magnificent, and you as a person pale into insignificance on standing next to it. You wonder how come this body of nature, and in the case of PD, this body of knowledge, how did it came to existence? And it is just such a sublime experience. But anyway, I digress. Yeah, the topic is huge, and your life is short, so choose your topic wisely and stick to it. Okay, and that's how we make progress. So, and that a corollary for that statement is stop looking for the most comprehensive and most encyclopedic textbook on PD. Is just such a futile task, because even though Evans's book is perhaps the most comprehensive on the market right now, it does not cover things like modeling. Okay, so it mostly just start with, okay, this is the PDE and let's deduce its properties. Okay, it works like that. But it rarely covers, okay, why are certain models valid in what situation, and there's not even a whole lot of derivations of PDE. So let's say this is the PDE from this, for example, this is Navier-Stokes, but it does not derive, say, the origin, okay, the fluid mechanical, classical mechanical origin, because it's important. Like even in the field, say the fluid mechanics is so diverse, simply because the PDE that governs it, even though there's a single PDE called Navier-Stokes, the field of application are so wide that you need to look at so many different asymptotic regimes. Low Renault numbers, high Renault numbers, is it compressible, incompressible, that sort of thing. So even in the field of, just in the subfield, okay, of PDE, fluid dynamics, the techniques are so different. Okay, and let's say if you just start with a PDE, say, and say this is the PDE from gas dynamics, and you deduce a whole bunch of property, it does not mean you can. It is actually appropriate for your problem. So, so that's why, as an applied mathematician, you should always care about, say, where does a particular mathematical problem arises, and not just focus on, okay, how do I prove a bunch of theorems about it. Right? So Evans's book rarely covers the derivation, because simply due to the massive size of the book. I mean, the focus is on analysis of PD, which is totally okay. But My point is, stop looking for the most comprehensive text on PDE. It's just such an impossible task. And let's not forget, there's also the separate field on numerical PDE. So numerical PDE is also almost okay. It's a subject on its own. Okay, you can think of numerical PDE as a subject on its own, or you can think of it as a subfield of PDE or numerical analysis. Okay, numerical PDEs is once again a very interdisciplinary field. It's connected to all kinds of mathematics, both theoretical and more applied. It is a separate. I think numerical PDE is a separate field. It is so large, simply because computational fluid dynamics (CFD) is a separate field. I guess physics will do that kind of modeling well. Yeah, but the thing is, physics books and mathematical books, they have different level of rigor, right? So, and so yeah, I was saying, like, as applied mathematician, no book has the responsibility of being completely comprehensive. There's simply no such thing. What matters is, when it comes to the matter that it does cover, it does so well. I think that's the most important thing. At a certain point, you stop looking for the most self-contained, the most comprehensive, the most encyclopedic resource, because let's be honest, you're not going to read the whole thing, right? So it's all about the quality of presentation rather than the number of topics. It's all about quality over quantity, in my opinion, right? So yeah, numerical PDE, I was saying, CFD is its own. Already it is its own field, right? So, for example, the more example would be, say, the PDE in general relativity, Einstein's equation. Solving Einstein's equation is its own field, numerical relativity. Is this a tutorial directed to someone without rigor in ODE? Yes. So today we'll do some actual math. Well, PDEs, obviously, and it will only assume basic knowledge in multivariable calculus. Well, we will see some OD along the way, but we will derive pretty much from scratch. So that's the bare minimum of studying PDE. You need a good command in multivariable calculus, including vector calculus. Yeah, select one and focus on that, exactly. I mean, I'm probably not the best person to follow my own advice, because judging on the recent stream, I've did a whole bunch of diverse topic. But, you know, I'm a creator, right? If I just say, like, okay, we're gonna do Lawrence C. Evans's PDE walkthrough. You know, guys, what's gonna happen? I get like maybe 10,000 views maximum for the first episode, and then after 5 episodes, I get 200 views. It's just the way it is. I mean, I'm not saying I only care about views and whatnot. I mean, the thing is, as the subject matter gets more involved and so more intricate, and the number of people are able to follow gradually decreases. It's simply this is just the way it is, right? I'm not complaining. It's just the way it is. I mean, probably a lot of people are interested in the subject matter, but those who have the time and stamina to follow it through are rare. This is similar to many things in life, and that's okay. So that's why, although I do wish to concentrate myself, and I do wish to present various diverse fields of applied mathematics and also pure mathematics as well. I mean, this is a mostly applied channel, but one of the meta goals of this channel is to bring various disciplines together. So I do plan to do more pure fields, quote unquote pure, even though I in my opinion, the distinction is arbitrary. So anyway, these are the 2 books that I recommend in the more American Anglo tradition. Okay, so by the way, fun fact, Do you guys know a creator called Dr. Payam? He rarely posts video nowadays, which is a shame because I used to watch him a lot when he was posting. If he start repost, sorry, if he get back to YouTube, and I'll still watch him. I remember watching him a lot when I was a student. So do you guys know this person, Dr. Payam? So yeah, he's a professor in Brown's University. He's actual professor, okay, unlike me, with a PhD, unlike me. So he is a student of L.C. Evans. So he is a student of L.C. Evans actually, and his videos are amazing. You see, it's a shame that his last video was 7 months ago. Right, so he rarely posts video nowadays, which is a shame. But I remember watching him so much as a student in the university, like just a screen and a piece of paper and a pencil. Like while he was doing it like this, I'm doing the same thing on my end. Yeah, so he's a great YouTuber. I wish he can come back to posting more videos. See, and you see, a lot of his stuff are related to PDEs, ordinary differential equations. You see, mostly, you see, differential equations, calculus, maybe some linear algebra. I remember him having linear algebra videos, some real analysis, that kind of stuff. You see, mostly calculus related stuff. Yeah, mostly calculus related stuff. I mean, this is very natural for applied mathematician. The thing is, applied mathematics traditionally have so much stuff going on with analysis, you know, differential equations, probability, that kind of stuff. They're naturally, their foundations are analysis, right? So their foundation, I mean, I'm not a dedicated analyst, but simply because of the nature of applied mathematics, I know much more analysis compared to algebra, even though I don't consider myself a dedicated analyst. So yeah, his videos are amazing. You can learn a ton just from just working through, okay? You can't follow it like, say, if you're just, I mean, if you're very advanced, I mean, if you're a student, I was a student, right? When I was watching his video, I couldn't just play in the background and hoping to understand what's going on, or just eat dinner and watch the video and hopefully understand what's going on. You have to pull out a piece of paper and follow the argument and do whatever he's doing on the blackboard. So that's just the style. Okay, I think, yeah, it's fair to say that Dr. Payam and who's that? The other guy, Black Pen, Red Pen. Black Pen, Red Pen, and also Michael Pen were the three creators that I watched the most when I was in university. And I think and also Math Sorcerer, he used to do a lot of math as well. But later on, he switched to other activities, which is to my disappointment. Anyway, but that's his channel. He can do whatever he wants. Right, but the thing is, I like classical mathematics. Just a guy with a board and pure knowledge came out of almost nothing. This is just one of the most staggering sort of experience of doing mathematics. Anyway, so enough of that. Let me close this up. Coming back to more books I wish to recommend. So this is going to be the series of Russian text. Okay, yeah, Black Pen, Red Pen is still posting. Let me catch up with chat. So here, hang on. So, oh wow, chat is going like crazy. I have to come back to chat. So here it says. Yay, PDE. Thank you, Lockheed, for joining the stream. Oh, the Korean guy. Sorry, I really can't pronounce your name. You've been supporting the channel a lot. Thank you so much. And yeah, actually, you know what? I remember your interest in mechanics, in geometry, differential geometry, and classical mechanics. And guess what? Right now we have a series on tensor calculus. Maybe that will interest you. And yeah, perhaps we'll do some mathematical classical mechanics in the modern way in the near future as well. So hopefully we'll have some fun there. We're not. Yeah, it's a separate field. Yeah, there's so many distinct subfield in PDE. I mean, I lamented over hyper specialization in the past stream, but I'm not an idealist. I understand math is so huge, it's so complicated. You know, if you wish to make original contribution, you have to specialize in some way. You can't just hope like everybody nowadays still work like Euler. It's just unrealistic, right? What I am against is hyper specialization at a very early stage. At a very early stage, starting from first year in university, I feel that kind of unnecessary. Okay, so yeah, so Lockheed says, for me, all I want is something that is not the heat equation all over again. Exactly. I mean, you can, like for example, Evans's text. It's pretty comprehensive. Go check it out. It's not just not just PDE from mathematical physics alone. Okay. For example, you have the Hamilton-Jacobi equation, Hamilton-Jacobi-Bellman's equation, HJB, from calculus of variation and control theory. So check that out. So here I've seen the derivation of Schwarzschild metric, and it's a bit scary. Actually, you know what? Right now we're in the subject of tensor calculus on the channel, of classical, aka classical tensor analysis, and the goal is to understand curvature. That's the most immediate goal. So after that, the series will come to an end. I mean, not an end, but a pause. That will be like the first part of the stream, and I'll come up with a more compact, a more well structured series on the foundation of tensor calculus. And after that, if I see some interest, we'll probably see some things like maybe classical differential geometry and general relativity, which is I always wanted to learn, but I didn't have time to do so. So now as a math creator, I mean, I'm not doing this full time, not yet, okay, not with substantially more financial support, but I do wish to have an understanding over these areas. So Vernon says, I studied an ODE course, but the content was so minimal. I suppose it's for people who just want to get the degree. I don't know. That's unfortunate because ODE is there's no shortage of content. Okay, there's no shortage of content in the field of ODE too, even from an elementary perspective. So yeah, if you want, Vernon, perhaps, I mean, this is tangential to the subject of this stream. We will perhaps do an ODE stream later. ODE, PDE, SDE, all kinds of differential equation, dynamical system is the lifeblood of applied mathematics. So each of them deserve its own, not just video, but perhaps series. But once again, it's very difficult to be a one-man department. Okay, study ODE as well, but the intersection between ODE and PDE should be minimal. Same for, should be minimal? I don't know about that. I think you should at least have a basic knowledge about ODE to solve PDE, because you guess what? Guess what? PDE itself inspired a whole field of ODE called boundary value problems. Right? Called boundary value problems. I don't know if on average, in my opinion, no, actually. But based on my experience, my course on ODE in the university, the first course on ODE in university does not cover boundary value problem a lot. Okay, it was barely mentioned, but most of the time we were solving for general solutions or initial value problems. So boundary value problem was pretty much a separate field of ODE that is, so to say, driven by the study of PDE. So ODE and PDE are very much related. Okay, even though at advanced research level, the things they care about tends to be diverse, but if you wanted to get started with partial differential equation, you need some basic knowledge of OD. Otherwise, you can't solve anything. Okay. SD, stochastic differential equation. Yes, stochastic differential equation is, of course, a subfield of stochastic calculus. We already seen one on the channel. I posted one video. Not dedicated to stochastic differential equation, but we did geometric Brownian motion. Geometric Brownian motion is arguably the simplest, non-trivial stochastic differential equation, and it is still one of the most fundamental model when it comes to financial modeling. It's not perfect, and it's by far from it, but it underlies fundamental formulas such as Black-Scholes. And speaking of which, I promised people on my Discord we will do a Black-Scholes stream just from start to finish. The idea of option pricing, and yeah, the Black-Scholes PDE, the solution to Black-Scholes PDE, and etc. So yeah, this is something we'll do down the road, hopefully soon. Okay, I don't know. It's improbable to run out of things to say on YouTube. I mean, I don't know about that. But the thing is, like, even if you just do the same material, even if, let's say, if you just do the same material, it will still be like new content. It will still be new. I mean, the mathematical notion can be the same, but the presentation can be new. Guess what? New books on PDE, new books on elementary PDE still come out every year. Like, I mean, insert any math subject here. The thing is, even if you're just talking about the same subject, there's still things to talk about. There's no such thing as running out of things to say about mathematics. There's objectively no such thing. Like for perhaps for people in other fields, it might feel weird that why do mathematicians write about the same damn thing over and over? Think about how many different textbooks on calculus there are. Are they just pointless? No, not at all. Right. So anyway, there's no such thing as running out of things on YouTube or saying, I mean, this YouTube is irrelevant. The thing is, it's impossible to run out of things to say about math. Okay, yeah, so I was saying, for me, applied math book just looks like analysis, calculus, and linear algebra. Yes, that's very much true. That's very much true. I mean, to a great extent, and that's classical applied mathematics. So for applied mathematics, I think it's fair to, I mean, perhaps that's not fair, but that's my opinion based on my observation. So applied math can be roughly divided into three big areas. So you got dynamical system, all kinds of differential equations, ODE, PDE, SDE, and there's also a new, I mean, relatively new field called delayed differential equation, DDE, all kinds of differential equation, but also there are discrete counterparts, namely difference equations. Okay, and the second big area is numerical methods, all sorts of computational mathematics. Okay, and the third one would be optimization. So optimization, well, optimal control is part of optimization. Of course, these are interconnected, but roughly speaking, they can be seen as distinct fields with their own priorities. Okay, so all of them requires extensive analysis. All of them requires extensive analysis, all kinds of analysis, real analysis, complex analysis, functional analysis, measure theory, and the list goes on. Right. So, and comparatively speaking, much less algebra. I mean, I'm not saying no algebra whatsoever. That's completely not true. But relatively speaking, if you're planning to be an applied mathematician, you should spend more time, at least initially, on analysis than algebra. Right. So yeah, definitely more analysis heavy on this channel. So actually, you know what, guys, I was I was referred to as the quote unquote analysis kind of guy. Me personally, I was referred to as quote unquote the analysis kind of guy on the channel called JC Practice Math. So do you guys know him? JC Practices Math. Sorry guys, I mean I was planning to do actual math right from the beginning, but we'll do so at 9. Okay, sorry guys. I just want to talk to you guys about various things. And here, this channel, this one is great. JC Practices Math. So during one of his live stream, in which I was in the chat, so he referred to me as kind of analysis kind of guy. So he was a software engineer from Google and others, and now he's coming back to. I believe he was a math major and a computer science major. I don't know. Yeah, he was a bachelor. He was a bachelor in math, but he did software stuff after he graduated, and now he is coming back to math, which is awesome. And he has a series on introduction to pure math, introduction to pure or math. Actually, this playlist as well, math as a hobby. Math can be a hobby, based on the book by Serge Lang called Basic Mathematics. So this is really back to the basics. Okay, I mean, I made one video on introduction to proof. I mean, not video, but live on introduction to proof. But if you really want to say learn the foundations of say where's the intro to pure math series? Actually, this one, right? Yeah, I think it should be this one. Yeah, this one. Math can be a hobby. Intro to pure math. Yes, this one. This one. So he really started from the most fundamental stuff. I mean, I call my introduction to proof fundamental, but perhaps this is still not for complete beginners, even though I did not call for any particular prerequisite, but there's still a degree of maturity that is needed to follow it. So, but because, I mean, I'll justify my decision. But the thing is, if you want to learn proofwriting from scratch, go ahead and follow JC. Okay, so this is a great series in its making, and I can confirm it. The thing is, my vision on introduction to proof is very much single-minded. Okay, I just want people to be able to follow text on analysis, rigorous probability theory, that kind of thing, as soon as possible. Because so JC comes from a more software background, so he had this. I mean, he had even admitted on stream. The thing is, he admitted that he is biased towards more discrete mathematics and abstract algebra, which is totally fine. I mean, which is nothing wrong at all. Those fields are absolutely beautiful. But me coming from a more applied and stat background, I mean, like calculus for me is the crown jewel. Calculus analysis is the crown jewel. So, and because I figured a lot of people who wanted to see more in-depth stats don't have a math background. Okay, so some people, a lot of people, due to the popularization of data science, machine learning, that kind of thing, I think a lot of people are right now much more interested in, say, probability theory and optimization, mathematical statistics a lot. But for that, you need to read the books. Okay, to read the books in those areas, you really need a proof foundation that is closer to analysis rather than algebra. That's my take. All right. So my goal for introduction to proof is to get people to get people to be able to read books like Baby Rudin as soon as possible and minimize digression. So the goal is very much single-minded. However, JC's approach is much more comprehensive. You see, he really started from the the very beginning, like starting from just arithmetics. Okay, I don't have patience for that. Okay, I don't. It's just like and I admit like this is completely a more totally legitimately a more balanced approach. So, and if you're interested in a more discrete side of mathematics, definitely go follow him because I have just fewer things to say about them. Okay. Anyway, so coming back to yeah, sorry. Okay, where are we going? So coming back to the books on PDE, there's a few Russian texts which I'd like to recommend. So here, the first one I would recommend is actually a free book. This is a book that is in the description of the live stream. This book is in the description of the live stream. PDE, online textbook for APM 346 by Professor Victor Ivry. So APM 364 is the standard introduction to partial differential equations at the University of Toronto. Professor Victor Ivry is a professor at University of Toronto. So I'll come back to chat in a bit. Okay, I'll finish discussing these tabs. Okay, so Professor Victor Ivry, this is his Wikipedia. He's a Russian-Canadian mathematician specializing in analysis, micro-local analysis, spectral theory, and PDE. So he's very much an expert in that. And his doctoral advisor was Sergei Sobolev. So I guess no more introduction is needed. But here, this is his contribution. As you can see, it's very much related to mathematical physics. Weakly hyperbolic equations, propagation of singularities. Interesting, because he was invited to give a talk at ICM in 1978 while he was still in the USSR, but was not granted an exit visa by the Soviet authorities. Okay, interesting. So yeah, this is his work, and that's his textbook, and it's completely free. Go check it out. It's in the stream description. Actually, you know what? If you're watching it from a mobile, I'll put it in chat as well. So this is Ivry's text. Professor V. Ivry. Textbook on PDE, on Introduction to PDE. All right. So this one, why do I recommend this one? Say over, I mean not over, but rather as compared to Haberman. So Haberman is a great book, don't get me wrong. But this one here, Ivry's text, I think it's a nice bridge between more elementary material and more advanced topics. So for example, you still got the standard material, heat equation, separation of variables, things like that. Okay, but it also has more advanced topics such as variational methods and distributions. So if you're a physicist, you probably know the object called the Dirac delta function, right? And the mathematical theory that formalizes notions such as the Dirac delta is called distribution. So you can think of a distribution as a ultra generalization of differentiation. Right? So you can differentiate all kinds of wild stuff using the theory of distribution. And you have also a discussion on eigenvalues and eigenfunction. This is a very advanced topic, actually. Asymptotic distribution of eigenvalues. You say, oh, why is eigenvalue, eigenfunction doing here? This isn't supposed to be a course on PDE. Isn't this linear algebra? Yes. So in PDE, we see a great analogy between the finite dimensional linear space, the study of linear algebra, as well as infinite dimensional linear space. So PDE is a great gateway towards functional analysis. So you can think of a large portion of functional analysis as infinite dimensional linear algebra. And in PDE, we also see notions of eigenvalues because of separation of variables. So separation of variables gives rise to eigenvalues and eigenvectors, or more appropriately, eigenfunction in infinite dimensional setting. It's very beautiful and it's extremely powerful. So there was this famous problem called "Can you hear the shape of the drum?" You guys might have heard of it, called "Can you hear the shape of the drum?" So it turns out that if the drum's frequency are eigenvalues, and "Can you hear the shape of a drum?" is essentially saying, can you tell the shape of the drum based on its spectrum or eigenvalues? And the answer turns out to be negative, and it spawned a huge area right now called spectral geometry. So this is an introduction to spectral geometry, and this is a very advanced topic, and it is included in the very first course on PDE. So this book, in my opinion, is a great bridge between more elementary treatment and current research. So this is a great one, and it's completely free. It's got tons of exercises. Okay, so look at this one. So yeah, this is one problem, by the way. This is one problem, and you have to go. You got to solve 10 PDEs. I mean, not solve here, you just classify them, right? But later on, the problems are also like that. Just let's say a 1D wave equation. Let's take a look at this. Is problem to section 2.1. There's tons of exercises. Like if you don't want to pay actual money for an actual book, for a physical book, this one is, I think, is a great substitute. Okay, although it is more dense. Let's be honest, this is Russian tradition after all. It's denser than, say, Haberman. Haberman is very approachable. Haberman is designed for mass adaptation. So it's very approachable, and the pace is slower. Okay, so great compliment. Okay, so this one by Ivry, strongly recommended. It's in the stream description. And actually, here we'll answer a great question. That is to say, do you need to do a lot of proof in PDE? Not at an introductory level. Not at an introductory level, because Ivry has an explanation. Because I was asked yesterday in my Discord, last night, saying, do I need a real analysis for differential equation? I answered yes. For rigorous study of differential equations, doesn't matter which type of differential equation, you need real analysis. Even the simplest ODE, rigorous, okay, even the most basic but rigorous treatment of ODE requires real analysis, let alone PDE and SDE. So here it says, in this class, it will be very few theorems. Proofs will not be very rigorous. Reason is very simple. Look at ODE class. There are just two existent uniqueness theorems for the Cauchy problem, and they require arguments basically from real analysis. In PDEs, there are many existent uniqueness theorems for different types of equations and different problems for them, but not only proofs for such theorems require much more advanced arguments, but even accurate statement of these theorems require much more advanced notions. Basically, one needs to study advanced or very advanced real analysis before taking PDE class, but this is not feasible even for a mathematics specialist. Okay, a mathematical specialist is a program at University of Toronto. So basically, those guys are crazy. Those guys pretty much complete a grad program in their undergrad. Okay, so the mathematical specialist program at University of Toronto have insane courses. Their third and fourth year courses are pretty much grad course. So these guys use Evans in their third year. So this is what Ivry mean by mathematical. This is a jargon within U of T, University of Toronto. Like, to do rigorous PDE, okay, just give you an idea what rigorous PDE looks like. Okay, here, go to MIT OCW, rigorous PDE. Oh, okay, no, not this one. MIT OCW, best website in the entire world, much better than YouTube for sure. So yeah, if you want to do math, turn off the stream, go here and just like, yeah, seriously. Differential analysis is the title for rigorous PDE. Differential analysis, graduate level. So you got to complete the first module on differential analysis to do rigorous PDE. This is rigorous PDE. In this course, we study elliptic PDE with variable coefficients building up to minimal surface equation. Well, minimal surface equation is a PDE that came from calculus of variation as well as differential geometry. So here, yeah, this is very much a rigorous PDE course. If you look at the lecture notes, review of harmonic function perspective we take on PDE. Sobolev inequalities using functional analysis. So you need functional analysis already. This assumes mastery in functional analysis. So let's just take a look, for example, the first lecture notes. Can we zoom in? Yeah, like this. Okay, this is perhaps still more elementary stuff. Okay, download this. Okay, download this and check it out. So basically, heavy analysis to do any sort of rigorous differential equations. Okay, let me close this up. Okay, so yeah, I'll put it in chat. This is rigorous PDE. Rigorous PDE. Course. Right here. Go check this out if you want to see what sort of background you need to do PDE and ODE rigorously. Okay, so that's why here we don't prove theorems. Okay, we don't prove theorems here in the Introduction to PDE course. Okay, and speaking of Sobolev, to those who don't know, was just an unavoidable figure when you want to talk about modern PDE. So he was known for a notion called Sobolev spaces. So what the heck are Sobolev spaces? So Sobolev spaces are sets of functions, that has well, let's just say certain properties, because I mean there's little point of going into the technical details here. Sobolev spaces are special kinds of function spaces that which we consider as the range where solutions are selected. Okay, so as it turns out that classical solutions of PDE, differentiable functions, continuously differentiable functions, are unsuitable for many PDEs. However, the PDE themselves should still be physically meaningful. Okay, so how do we cook up non-solution in the classical sense but still have physical meaning? You need Sobolev spaces. So now Sobolev spaces is an abstract field in functional analysis on its own, but it was originally invented to solve PDEs. So this is Sergei Sobolev. Sobolev was also, just a very productive individual. He was the founder and the first director of the Institute of Mathematics at Akademgorodok. Akademgorodok is a region in Russia. Is a region in Russia in the city of Novosibirsk, because it's inside Siberia. In Russian, literally means academy city. So it's a dedicated city for scientific research, which was later bear his name. Okay, and played an important role in the establishment, in the development of Novosibirsk State University. And Professor Ivry was a graduate from there. Okay, so yeah, he led the Soviet, participated in the Soviet nuclear project, as many scientists of his caliber did, including Kolmogorov and etc. So yeah, that's Sergei Sobolev. And two more Russian texts, actually just one more. Well, actually, you know what? Two more. Because Sobolev also wrote an introductory book on PDE. In typical Russian tradition, it bridges the elementary and more advanced topic. So this one, called Partial Differential Equation in Mathematical Physics. This one actually, even though the topics themselves are elementary, so things like heat equation, wave equation, that kind of thing, but the level of analysis is highly modern. Okay, it actually includes a mini course in this book. Okay, in this book, it actually contains a mini course on measure theory, and also techniques such as functional analysis and integral equation. So these aren't dedicated courses, but they were introduced on a need-to-know basis here. So if you wanted to see, if you lack the formidable analysis background to do rigorous PDE, check out this book, because it does not assume a lot, and it introduces the advanced notions along the way. Here, AI Overview, in my opinion, is actually pretty accurate. I have this book as a physical copy. Yeah, it introduces Lebesgue integration, basically measure theory, integration, and integral equation. Integral equation was one of the main reason that functional analysis was invented. So the thing is, you can convert differential equations to integral equations, often through the means of Green's function. And then you can use the techniques in functional analysis to study the equivalent integral equation. For expansion, we've seen that already. Right, so yeah, it is very much directed, well, in the name, for mathematical physics. So this one is great, and I think it has a Mirror page. Yeah, so Mirror was a Soviet publisher that translates the classical works in the Soviet Union to English. However, this publisher, I don't think it actually exists, but it'll no longer exist. But many of the books were preserved, well, on Internet Archive. But I mean, the book here, this book is now, it has a Dover edition. Yeah, this is the cover of Dover edition, so it's very cheap. So feel free. I think it's fair. I think you should get one. I mean, just my personal bias. If you're serious about PDE, go check this one out. Written by one of the founders of just modern PDE. Like, it's totally worth it. Here, these are the topics here. Oh, by the way, interesting terminology is called Ostrogradski formula. Ostrogradski formula is what we call in the West Gauss's divergence theorem, but the Russians actually, that's actually perhaps the more accurate term, the attribution, because Gauss, people already know that before Gauss. I didn't know whether Ostrogradski was the first one to discover it, but anyway, this is divergence theorem in Russia. Lecture 1, derivations of fundamental equations, starting from physical principle. Formulation of problems of mathematical physics. Hadamard's example. So here is already in lecture 2, the modern priority of study. The modern priority of study, that is not the search of specific solution, but rather the question of well-posedness, is given in lecture 2. Extremely rare for introductory courses are concerned. The current biggest puzzle on PDE, arguably so, is the Navier-Stokes equation. Right? The Navier-Stokes equation from fluid mechanics, and the and what's that? And the main question is well-posedness, existence, uniqueness, and smoothness. And you will see what this means in lecture 2. Lecture 3, classification of linear equations of the second order. Yeah, this is very much standard stuff. Equation for the vibrating string, wave equation, and a solution by the D'Alembert's method. Riemann's method. So this is also in the domain of wave equation, more generally hyperbolic equations, and it has applications in gas dynamics. Here, this is a mini course on measure theory I was talking about. Lecture 6, multiple integrals, Lebesgue integration. So, yeah, so this is, we're doing it as a full series. Okay, we're taking things slowly. This is the notion of Lebesgue integration as a mini course in a book on PDE. So this is classic Russian style, actually. Very little artificial artificial separation between pure and applied mathematics. A PDE prof just casually give you a course on measure theory and move on with, well, more PDEs. Integrals depending on a parameter. Okay, equation of heat conduction. This is a heat equation, Laplace equation, and Poisson equation. So these are steady state solution of heat equation. Laplace equation is of course also connected to complex variables. General consequence of the Green's formula. Green's formula, is it Green's function? I don't know. Poisson equation, unbounded medium, Newtonian potential, more mathematical physics, solution of the Dirichlet problem for a sphere, Dirichlet problem and Neumann problem in half space, wave equation. Right? So this is the new, perhaps more unique feature. It's called the theory of integral equation. The theory of integral equation, once again, integral equation is its own distinct field. Here you're just given a mini course on integral equation on need-to-know basis. You're basically converting differential equation to integral equations and then use techniques from functional analysis to analyze them. Okay. Application of the theory of Fredholm equations, so that's an integral equation, to the solution to Dirichlet and Neumann problems. These are original formulation of PDE. Green's function for the Laplace operator, Fourier methods, etc. Hilbert-Schmidt theorem. This is also again functional analysis. Hilbert-Schmidt theorem is a result in Hilbert space. That's functional analysis. So as you can see, in typical Russian tradition, they like to bridge the pure and applied and more elementary and advanced stuff. Okay, so there are actually another two books, but a set of actually it should be more appropriately understood as one book. I'll explain what I mean. Whereas in reality there are two. So this one by Tikhonov and Samarsky is called Equation of Mathematical Physics. Equation of Mathematical Physics, written by Tikhonov and Samarsky, as I was saying. So this one is more physically oriented, but don't get me wrong, the rigor is relentless. The rigor is relentless. So the Russian books are known for their extreme rigor, but at the same time not in a Bourbachian way. Okay, they do not pursue rigor as its own end. Okay, they do not pursue rigor or abstraction as a merit on its own. Even though the proofs are rigorous, they always seem to motivate the material, as well as pair this with deeply intuitive commentaries. Like, what does this actually mean? Right, so that kind of stuff. So if you're interested in deep understanding, I think Russian texts in general will make you very happy. So Andrei Tikhonov was a topologist, functional analyst, mathematical physicist, and ill-posed problems, also known as inverse problems. So once again, you see his work straddles both quote-unquote pure and applied mathematics. Okay, for these people, the distinction is arbitrary. Okay, of course, if you're taking, say, a course in topology, if you're taking a course on topology, you'll see the notions as Tikhonov spaces, a kind of topological spaces. And if you're taking, say, data science on machine learning, you will see the notion of Tikhonov regularization. Its simplest example shows up even in linear regression. So Tikhonov regularization. So basically, you wish to restrict the classes of models that are admissible and punishes models that are pathological. Right? So it's also called ridge regression, as I was saying. Ridge regression is Tikhonov regularization in the context of linear regression, but it's a much more general technique. Okay. Once again, this sort of method, Tikhonov regularization, the understanding, the invention of these results are simply impossible without a fundamental understanding of functional analysis. So Tikhonov regularization is it's a widely used method for regularization of ill-posed problems. And Tikhonov himself was widely considered as the founder of modern inverse theory. And Samarsky was a Russian numerical analyst, one of the representative of the Russian school of numerical analysis. And to this day, I don't think all of his works are translated because he wrote so much stuff. Um, he was a soldier during the Second World War and was severely wounded in the Battle of Moscow. But luckily he survived, and he worked with Tikhonov on mathematical modeling of nuclear weapon explosions and electromagnetic fields of waveguide. Okay. So yeah, he was a very productive individual. Yeah, so not all of his books were translated. So this one by Tikhonov and Samarsky has a corresponding problem book. That serves as its companion, called A Collection of Problems in Mathematical Physics. Once again, a Dover book. You see, the problem book itself is 768 pages. How crazy is that? Like, the Russians certainly don't mess around. So this one is also, you should probably get this one if you decide to get this one. Okay, they go together. And one idiosyncrasy about Russian texts is that, I mean, not always, okay, and perhaps nowadays less common, but during Soviet time, math textbooks and the corresponding problem books are separate, perhaps for the reason of keeping the volumes more manageable. Because this one, Equation of Mathematical Physics itself, is over 700 pages, and the problem books is also 700 pages, and if you put them in one, it will be a monster. Right, so they're, I mean, separate monsters, but still, if you combine them, it will be completely unmanageable. So the Russians tend to separate the lecture notes or the main textbook with the problem book. Right? I mean, which works for Russian students, I guess, but for foreigners, this is an inconvenience because sometimes only the textbook is translated and not the problem book. And you need exercises to master mathematics. And luckily in this case, the translation for both the main text and the problems are available. The book by Sobolev, however, unfortunately only has main text. It does not have exercises, sadly. Perhaps pair this one with Evans, I don't know. But the thing is, like, if you decide to become, say, you want to do mathematical research, right? So a lot of your activity constitutes of reading papers, right? And papers typically don't have exercises. So how do you know you understand the actual material, right? Without author explicitly giving you exercises. This is a great practice. And I think the only benchmark is see if you can rederive everything from scratch. And in the process of doing so, you will appreciate what step is quote-unquote unnatural, which probably means there are still things you haven't not yet understand, and then move on. Right. So this is a great exercise for saying like reading monograph. This is really a textbook, but it is written in a style of a monograph, like research monograph. So wow, that was like an hour-long introduction on just book alone. Okay, I mean, I think it's justified because the field is so large, and if I just jump straight into the math, it could be interesting, but it would still, I guess, probably for beginner, you need to decide where you spend your energy on, right? And what would be a general roadmap for the field. I think this is justified time spending. Okay, I apologize if you're here for actual math and I'm here just talking about all various books on a superficial level. Hopefully, you can forgive me. All right, so let me catch up with chat. My goodness. Okay, so let me catch up with chat. So where were we last time? I was behind. Book tour, I know, right? Sorry about that. I promise I would not do this very often because, I mean, guys, PDE cannot be a standalone stream. Like, are you kidding? Like, I mean, I'm not going to just do one standalone stream on PDE, am I? This is just, like, does not do the justice of the field. Okay, we will have a lot more time doing actual PDEs in the future. Lockheed asks, how does modern classical mechanics here, let me just pull chat here. How does classical, where is it? guys? How does modern classical mechanics look like? Genuinely curious, since only know classical mechanics from high school. Guys, modern classical mechanics will blow your mind. Let me just go to this text called The Foundational Mechanics, not Foundational Machine Learning, Foundational Mechanics by Marsden and Abraham, I believe. Foundational Mechanics, this one, and also Arnold's, Vladimir Arnold. You see, I always do things in a balanced manner. One American, one Russian. So Arnold, Mathematical Methods of Classical Mechanics. So in a nutshell, modern classical mechanics is a subfield of, where's chat? Where did I? Yeah, modern classical mechanics is a subfield of differential geometry. So things are formulated in terms of smooth manifold differential forms and Lie groups. Okay, so that's the modern formulation of classical mechanics. It's highly geometrical. Okay, parallel situation happens in functional analysis. So basically, not functional, but quantum mechanics. In my limited understanding, quantum mechanics is formulated using the Hilbert spaces. Okay, basically applied functional analysis. So you need differential geometry. Here, where is that? Yeah, differential geometry to do quantum mechanics. And you need you need functional analysis to do quantum mechanics, just like you need differential geometry to do modern classical mechanics. And where's the list of content here? I mean, this book is available for free, but I don't want to get into trouble with copyright. So let's just take a look at the content. Okay, so the content here, list of content. Come on. Yeah, this was Lagrangian mechanics. The Lagrangian formulation is formulated on a manifold. So the dynamics now takes place on the so-called configuration space, which is a manifold, high-dimensional generalization of surfaces, rigid bodies, Hamiltonian mechanics, differential forms, symplectic manifolds. This is what it's about. Classical mechanics in a modern formulation is a sub-branch of differential geometry. And I think Spivak, yeah, you guys probably know Spivak. Spivak also has a more elementary introduction to that. So yeah, and this is Arnold's text on the so what's that? Classical mechanics. A Western counterpart with more details would be Foundational Mechanics by Abraham and Marsden. Foundational Mechanics, second edition from Caltech. So yeah, it's once again application of differential geometry and differential topology. Okay, so I will not click on this one because it takes forever to load. This is a massive file. Modern mathematical classical mechanics. Perhaps we will spend some time on it. It's very beautiful. So not about national strategy of not attending courses in union and focus on just publishing from freshman year. Well, I don't think it would work for most people. Let's just put it that way. The thing is, I mean, like most people aren't just that motivated, right? So I think, I mean, perhaps the best use of university is to build connection. Okay, I know there's a lot of cynicism surrounding academia and courses and whatnot, but still, I mean, they're still very valuable. The content themselves, I believe, are still very solid. What the problem arises when you grade, okay, when you evaluate. This is where the problem arises. The current dominant evaluation scheme prioritizes root manipulation and conformity rather than deep understanding. Right? This is also quite indisputable and quite widely acknowledged even among professors themselves. So the problem is not with the course content, There's nothing wrong with, say, learning linear algebra from a university courses. The content are amazing. The problem is, does the grading scheme actually reward understanding or just repetition? That's the problem. Right? So anyway, so if you like, let's say, if you the I don't think this method works for most people. Right? Just make the best out of your university experience and distinguish, so to say, certain elements that is this, and try to separate, okay, certain elements that is perhaps not in your best interest. Okay. So here, what about algebraic geometry? Not qualified to discuss, sorry, because algebra background very weak. Hey Ming, just let you know that your video, oh, thank you so much. Well, I don't think I published much video on PDE solution. I'll make that up later. I have that book, Black-Scholes Crashed Our Economy. Maybe. But certainly, you know, the geometric Brownian motion does not capture things like extreme events. Geometric Brownian motion is a continuous model. It does not model things like a shock in the economy very well. So yeah, take Black-Scholes with a heavy grain of salt. But the fundamental principle behind Black-Scholes, like the arbitrary, no arbitrary principle that so to say, give rise to the Black-Scholes formula is still the backbone. There's nothing wrong with that. Well, perhaps that's a controversy as well, but perhaps it's less wrong than Black-Scholes formula because it is a very idealized model. So yeah. Can confirm JC is epic. Yeah, it's a very good creator. Go follow him. Follow him, especially if you wish to take a more balanced approach, as I was saying, towards the foundation of mathematics. I mean, this channel is very much, even though I said I wanted to bring the fields together, the different disciplines together, it is still biased towards more advanced, sorry, not advanced, but applied, okay, applied topics. Yeah, optimization is great. Optimization is super interesting. So thoughts on quant finance. Thoughts on quant finance is it's a great field. It's beautiful. It's beautiful. What else can I say? I'm not a quant, first of all. I'm not a quant, but I think stochastic calculus is worth your time. Well, we cover sublib spaces. I don't know, like this is PDE for beginners. So sublib spaces would probably not in the near future. Okay, but we can say, for example, we will do, at least I hope this year, we will do some numerical PDE, such as finite element methods. Okay, we'll do some numerical PDE and finite element method, and we will cover sublib spaces in a restrictive sense. Okay. In numerical PDE, we'll have to cover, numerical PDE, especially finite element method, we will cover sublib spaces in a restrictive sense, not sublib spaces in the full generality. So that's, I think, a reasonable goal for this year. Okay, yeah, hi, Ego. Specific took a PDE course, something like mathematical methods for engineer for this semester. I'm excited, really want to learn PDE. Yeah, go ahead. Yeah, you rock. Yeah, so what we're going to do actually is going to be very similar to, likely going to be very similar to this course, Math Method for Engineers, Separation of Variables, Fourier Transform, just standard toolboxes. Yeah, you really can't do anything in engineering without linear algebra. Exactly. Modern, I mean, except perhaps with the exception of, say, software engineering, modern engineering is built on the language of linear algebra and multivariable calculus. Okay, but let's say if you want to do software engineering, you probably need more discrete math. I do concede on that. Perhaps everything else, all the other engineering requires linear algebra and multivariable calculus. Advanced as in many simple concepts combining together to create a complex picture, or advanced in having reconnect neuron in the brain. So sorry, I didn't explain, so to say, more sort of quote-unquote elementary versus advanced. Okay, in the field of differential equations, in the field of differential equations in general, okay, ODE, SDE, and PDEs, what we call elementary doesn't mean easy. Okay, elementary simply means the study of solution methods. How do you write solution? How do you find solution in a closed form formula, or not really closed form formula, but just analytic solutions? Okay, elementary portion of differential equation constitutes of representing solutions by analytical means. It can be integration, it can be an infinite series, that kind of stuff. So you're still in the process of trying to solve particular problems in perhaps simple geometry using formulas. Okay, more advanced, quote unquote advanced, is in the sense of qualitative study. So, for example, where's Ivry's text? Ivry's text is here. Yeah. Going back, so separation of variable is considered an elementary topic because it is a method of solution. It aims to represent the solution as, well, an infinite series. So is Fourier transform. This is considered elementary topic in the field of PDE. However, let's say if we go to the notion of weak solution, the very notion of solution is now in the investigation, right? Because in the elementary setting, you just understand the solution as a function that satisfies the PDE. If you plug in the PDE, boom, it all checks out. It's an identity. So that's the domain of elementary study. The advanced portion is more qualitative. Okay, it does not mean you don't care about the solution as numbers anymore. You do, but it needs a stronger foundation. So there's more emphasis on qualitative question, like what do we mean by a solution? Because quite often what we call solutions in the field of PDEs aren't classical solutions. You can't just plug into the PDE and you get an identity. It has to be reinterpreted in some different ways. Okay, even in first order PDEs, this is already a problem. Okay. And of course, where we talk about Sobleb's text, right? Here in lecture 2. The lecture 2. So lecture 2, quote unquote, formulation of problems in mathematical physics. This has to do with quote unquote well-posedness. Well-posedness. Does the solution exist? In what sense? Is it unique? And does the solution depend on initial data and boundary data continuously? So these aren't problems regarding formulas of solution. Instead, we care about whether the problem itself is well posed. Okay, and once you have that foundation, you can solve with a quotation mark. You can solve PDEs using numerical and topological method, because there is no guarantee a priori guarantee that your formulation corresponds to first of all, your formulation of the problem bear any resemblance with real life. And the thing is, say if you simulate the solution of a PDE on a computer without analytic solution, okay, how do you know the discretized problem is a good representation of the continuous problem? These are qualitative problems, and they require advanced analysis to answer those questions. So this is what we call advanced. So you can think of another way to answer the question elementary versus advanced is that elementary only needs calculus. Elementary PDE only needs calculus. Elementary DEs, okay, ODEs also only needs calculus. But for advanced, you really need your background in analysis. Hopefully that makes sense. Okay, so yeah, thank you for a walkthrough. It's very pedagogical. Thank you very much. I'm glad to do this. So can you tackle the topic of PDE coupled with ODE, like set of two equations? Yes, you have. I mean, I'm not sure about PDE coupled with ODE, but typically you have coupled PDEs and coupled ODEs. But I don't know what it means to say PDE coupled with ODE. But definitely system of PDEs and system of ODEs are very common. Things like the Maxwell's equation from electrodynamics is an example of a coupled PDE. And of course, coupled ODEs are everywhere, even just in classical mechanics. Right? Newton's problem of gravitation, the Kepler's problem, let alone three-body problem, these are coupled ODEs. Also translated to Spanish, yes. Mir, the publisher Mir, which means peace or the world in Russian, translates classic Soviet texts to all kinds of languages: Arabic, French, Spanish, English, etc. So I have done a Master in Science in Computational Finance, previously studied economics. However, I'm missing Math Foundation, doing a year of math courses, functional vector complex analysis, ODE, PDE. You can always come back. You can always come back to do more math, just like JC. So, is this sufficient, or am I missing a module? This is one of the questions I said in the beginning. Stop looking for the most comprehensive, quote unquote sufficient text on PD, because it simply don't exist. The field is too large. It depends on your objective. Yeah. So how are you today? A lot of people on the stream today. Yeah, I'm very glad. PD is apparently a subject with great interest. We should definitely do more. It's so important, man. And it unites so many different fields. Yeah, I'm doing well, Sha. Thank you very much. So here's I use Zorich and 1 and 2 for real analysis. It's more complete. Yes, Zorich 1 and 2, in case you guys don't know. Mathematical analysis by Zorich. Vladimir Zorich, 2-volume. So the thing is, in Russia, there's no such thing as calculus. Okay, so let's say if we just search calculus, what's the Wikipedia page? Yeah, this is a calculus Wikipedia page, and if you go to Russian, по-русски, this is математический анализ, literally means mathematical analysis. So there's no word, okay, in Russian language, there's no word of calculus, or at least in the Russian mathematical language, calculus is just called mathematical analysis. So Zorich's analysis text is not meant to be, say, Baby Rudin in the Western sense, but it's supposed to be a first course on calculus. Think of this as Stewart on steroid. So basically, this is really phenomenal, okay, Vladimir Zorich. So his text on mathematical analysis is used for not just math major, but also physics and engineering, as far as I know, based on comments from people actually study in Russia and the Soviet Union, in the former Soviet region. Okay. His text on mathematical analysis is still very much the standard. So let's say if you feel Baby Rudin is rather unmotivated, go check out Zorich. So go check out Zorich's 2-volume, which is very, how should I put this? Just typical Russian style, very little distinction between abstraction and practicality. Okay, going back to chat. Chat says, here, let me finish this up. Okay, chat says, solution is learn Russian, getting caught out of my skill issue by a textbook. I mean, I'm learning Russian, but the thing is, I have to be honest, learning Russian is a moderately useful skill, okay, if you're a mathematician or a research mathematician. For a mathematician whose main concern is teaching, however, let's say if you're more interested in mathematical education, I think learning Russian is a lot more valuable. It is a lot more defensible position, a lot more defensible decision to learn Russian if you are interested in mathematical pedagogy, because Soviet pedagogy needs to be more widely, at least discussed. Okay, I'm not saying it should be widely more adopted, but at least it should be considered what the Russians were doing, and now are still doing. Okay, because the Soviet tradition is still very much alive. And just as an example, okay, in Russian or Soviet inspired institutions, Soviet influenced institution, oral exams is still the norm. They still do oral exams there. So let me just do a quick Google search on Russian math oral exams. Yeah, so yeah, this is the AI overview, and let me know this. I think this should be fairly accurate. The Russian oral exam is a rigorous testing method focused on deep theoretical understanding, rigorous proof, and live problem solving, rather than rote memorization. So historically prominent in Soviet universities, these exams require students to draw a ticket containing complex prompt, prepared notes, and verbally defend their mathematical reasoning in a panel of professors. So it's like an interview with a bunch of professors. You have to derive things from scratch, and people can stop you and ask you why you do certain things, and let's say challenge your position. This is unimaginable nowadays. I mean, at least from a Western standpoint, they still do this in Russia, by the way. You can have 15 to 30 minutes of silent preparation to write down definition, logical consequence, and geometric construction, and then present their derivation aloud on blackboard. In Russian, they say na daskie, or actually k daskie, to the board. K daskie. In Russian, just teacher say to student k daskie means to the blackboard, and do the derivations on live in front of everybody, facing intense questioning, counterexample, and logical checks from examiners. If you do this in a Western institution, I mean, if you do this in general, okay, perhaps not honored class is a different story. But if you do this to everyone, like department complaint to the department will skyrocket. It's just the way it is. And of course, there are some controversy surrounding that, because it is rumored that Jewish students were asked for super difficult questions. So it might look innocent looking. It might look like an innocent looking question, but Jewish students in particular suffer from this. They were given ridiculously difficult problems, and they were basically set up to fail, because anti-Semitism in the Soviet Union was a real thing, and doing oral exam was a nasty way, like a very subtle but nasty way to filter them out. So you see, in the West, we tend to so to say, more focus on standardized tests. There's a lot of criticism towards standardized tests. However, it does have this aim of fairness. Okay, the Russian tradition prioritizes deep understanding. They don't care if you survive or not. Okay, if you don't survive, just do something else. If you don't survive in the math department, do something else. That's the Russian point of view. But in the West, we tend to care a lot about building student confidence, which is again a noble goal, and at the same time try to minimize things like the coffin questions. Right? Try to be more fair to everyone. But at the same time, it has trade-offs. This is a world where we live in, right? There's no such thing as a free lunch. So if you use standardized tests, you're going to sacrifice conceptual depth. It's just the way it is. So it's our job as people who care about math and you want to really master math, to recognize the strengths and weaknesses in different systems. So yeah, like if you're a Jewish student, this will not give you a good time. Like the coffin question is very real. Okay. Anyway, so here let's continue with chat. So chat says, enjoy the permeable. Actually, studied physics in my undergrad, haven't touched it since then. I love this book. Okay, yeah, I'm glad you find them helpful. So, hey Ming, math can be self-learned? Yes, totally. Math can be self-learned. It just takes, I would say, self-learn. Even if you have a professor, Even if you have a professor registered in a university, the bulk of the work is still done by yourself. It is not taught. It's like a theorem that is handed to you. It's the theorem that is handed to you, but not seriously proved, is never the same as the one that you actually. I mean, I'm not saying proven from scratch, but the thing is, you learn it from a text, so to say, and then you reproduce it. So it's the bulk of the work of learning mathematics is still done by yourself. However, that being said, it does not mean you should study in complete isolation. Still, stay connected. Okay, stay connected. I mean, for example, in this community, in what's that, the MassTax Exchange. Well, MassTax Exchange is, I don't know, like you ask a question, like maybe you get an answer 5 years later. Like it's also a possibility, but try to stay connected. It's difficult to get feedback in math. That's true, but a lot of math study is about self-sufficiency. That's part of the quote unquote math maturity, because like and my Intro to Proof live and its follow-up are meant to make people, not make, but help people pick up self-learning skills. So basically, can math be self-learned? Yes, totally yes. So to do so, you need a lot of patience and a lot of time. Let's be honest. And as in the technical front, you need a proof writing and reading skill. So it can be totally self-learned, but especially if you're a complete beginner, it's nice to have some feedback. Okay, yeah. So pursuing CS, wanted to learn math. Actually, if you're pursuing CS and want to learn math, go follow JC. Yeah, he worked as a software engineer and is now coming back to math. His channel is arguably perhaps more suitable for you than my own. Okay, but please don't unsubscribe. Okay, okay, thank you. I'm just pointing out creators that are perhaps more suitable for your purpose. My question really is, am I making a mistake not taking abstract algebra along these courses? No, no. So it really depends on your objective. First of all, I don't know, it's almost like a cliche now on the channel. I will always say, oh, it really depends on your purpose. Okay, okay, I try to hedge, not because I try to avoid criticism, but the thing is, you can still get a lot of done. I assume you're an applied mathematician. Okay, I assume you wanted to pursue in things like applied mathematics and probability, stats, data science, that sort of thing, which is the main focus of this channel. You can still get away with not knowing abstract algebra for the most part. Okay, like even to this day, you can get away with not knowing a whole lot of abstract algebra. Linear algebra, multivariable calculus are still the foundational pillars of applied mathematics. I mean, abstract algebra is like a cherry on top for applied mathematician. Okay, so a professor of mine explained university is a mine. You get what you can dig out. Exactly, you're totally correct. It's totally correct. It's a minefield. I mean, it's not a minefield. My goodness, that's a terrible phrase. It's a mine. It's a field of resources. It's a field of resources. You can build connections. You can get knowledge from there. But you see, if you just want to get the diploma, you get a very superficial experience of a university career. So, which is, I guess, also valid if that's all you care about. You know, I'm not trying to tell you what you should care about, but university is definitely more than that. How about different PDE boundary condition and its role in possible solution? Yes, PDE boundary conditions are crucial. The same PDE, different boundary conditions can lead to wildly different solutions. So that's why we have the notion of Dirichlet problem, Neumann problem. These are classic boundary conditions. Changing the boundary condition changes the characteristic of solution a lot. Stewart on steroid. Okay. Oh, hi Leo. Thank you very much for tuning the stream. I hope you're still there. Russian math. I don't know if you like to take it slow and make sure you're understanding. Yes. I mean, I wouldn't say the Russian approach is slow because the courses are still very dense, and it's not like the Russians have more times than other people in the world, right? It it definitely the text feels slow, but the text feels slower because it has more in-depth discussion on the motivation and connection with the other field. I should really compile a list of Russian texts for various fields. I should really do that, and it's gonna be a big project actually. So yeah, I don't. I perhaps that's enough book recommendation for today. Okay, I think I already made my points quite clear. So, but I should really make a more comprehensive list of Russian text, let's say if you're interested in it. So starting from the most basic subjects like calculus, linear algebra, all the way to, I mean, I'll say all the way to the top because I don't know much about the top, but more advanced subjects, right? Like, so differential geometry, abstract algebra, functional analysis, what would be the Russian takes on those? Okay. Yeah, Leo, by the way, congrats on your new video. It's awesome. You deserve it. Okay, and here more. Oh, by the way, Levi, thank you very much for joining the stream. I forgot to acknowledge you because you are a very active member in JC's community. Thank you very much for joining my stream as well. So yeah, JC's basic math series is great. Is great. So regrettably my channel is perhaps not the best for complete beginners. Okay, regrettably, because I have so many requests, and I try to be, so to say, to accommodate those, and but at the same time, I do know fundamentals are extremely valuable, and even like when I cover things like the fundamental, I always learn new things. I still get new knowledge when I read linear algebra. This is just that. I mean, I still learn new things when I read Stewart's calculus from first year. I wish I could do more fundamental stuff, but right now there's a lot more requests, and I have on my own interest I want to pursue. So we'll try to see what we do about that. Okay. Yeah, there are applied fields where abstract algebra would be definitely helpful. Yeah, things like, hang on, what's that? Applied field cryptography, right? Leo knows a lot about cryptography, and abstract algebra, number theory is a must. These are traditionally areas applied mathematicians are weak in. Abstract algebra, number theory are absolutely crucial for fields like cryptography. Totally applied field. Are these necessary for mathematical finance? Actually, guys, if you are interested in mathematical finance, why don't we go to the University of Waterloo requirement for mathematical finance. Do Waterloo Math Finance. You will see what kind of courses they do there. Course requirement. Yeah, so this is an undergraduate program for mathematical finance. I'll just say this: you need quite some analysis there, but I don't think abstract algebra is required. Of course, you need to take like domain knowledge, right? Actual real science. This is ACSCI. Okay, it means actual real science. You see, investment science and corporate finance. This is our domain knowledge. But on the pure math side, you do need measure theory. I mean, measure theory is categorized as pure math, at least in Waterloo. So you need pure math there. Right? Yeah, so actually, pure math is considered the mandatory course. It complete all of the following. Real analysis and measure theory are mandatory. It's not just like a high-year elective. You must need it, and you must need stochastic processes, which I think is fair. Mathematical stats, applied linear modeling, stochastic process, and forecasting. For forecasting, this is basically time series analysis. Okay, and you'll see mathematics of financial market. This is where you see the basic stochastic calculus, Black-Scholes, that kind of stuff. You see derivative markets, options, that kind of stuff. This is actual real science, right? And compute one of the following. You need computational. So these are, you have choices here, but you need one computational course. Differential equations. So 250, 251, 350. These are all ODEs. Okay? Different options of ODE, and perhaps also optimization. You need a lot of math for mass finance, but once again, concentrated mostly in the area of analysis, not algebra. Algebra is not on the list, but definitely if you take algebra, that's a cherry on top. Okay, I'll just put the link in the chat. Okay, because a lot of people are interested in mass finance, because this is where the big money is at, right? So there you go. Go check it out. Here, where's, oh, здравствуйте, здравствуйте. Jesti, thank you very much for joining the stream. Здравствуйте, товарищи. Hello, comrade. So, here, where's, yeah. Yeah, it is true that Jewish students were systematically given harder questions. Yes, it happened to Edward Frankel. Exactly. This is not an isolated incident at all. So that sucked. That's totally unfair. You see, so this is what I was saying. Like, the Russian tradition prioritized depth in understanding, but it can also be abused. So it's all about, so to say, motivation, right? So is this where humans live? And we don't have the best system, quote unquote, the best system anywhere in the world. You guys probably know Sergey Brin, right? Sergey Brin was one of the founders of Google, and he was born in a Jewish family, and they decided they had enough in the Soviet Union and immigrated, which was a huge loss for the Soviet Union and Russia. And guess what, guys? Google now worth more. Google's stock value is Google's market value is bigger than Russia's entire GDP. So their empire now worth one search engine, basically. Yeah. So yeah, this is unfortunate, or fortunate, depending on your perspective, so to say. Yeah, here, anyway, a lot of. Any chance you could do Moisture stream at time in future current, and you can't really interact with the stream, perhaps run the poll. Okay, I'll do more randomized, okay, randomized stream of measure theory. Sorry. Yeah, I know it's just impossible to satisfy all the time zones. I'm sorry about that. So I'll make sure that the running series on the channel have their time randomized. Okay, so I don't bias. I mean, I hope try not to, but I try the best I can. Okay, but because I mean, I still need to sleep on regular hours, so I try to say, you know what, we'll do a morning and evening alternating. Okay, how about that? It will be difficult because now I'm on vacation, right? But after that, I only have time to stream on evening Eastern time. So maybe I can do like a super early in the morning. That would be, I mean, I can wake up at, I don't know, like 5 and do 3 hours till 9 where I go to regular work, and then I don't know, like perhaps that's an option, but we'll see about that. Because on Sunday is also difficult because I have personal responsibility. Sunday, I used to do Sunday stream, but nowadays Sunday is pretty much out of the question. I can't do Sunday anymore. So the only day I'm completely flexible. I wouldn't say completely, but the most flexible is on Saturday. So perhaps we'll leverage that. Um, Similar video on QFT, quantum field theory. I'm not even qualified to do that. I'm totally not qualified to do that. But you know what? We'll perhaps do more physics in general. I will just promise that way. Okay, we'll do more physics. Perhaps introduction to quantum theory from a more mathematician's point of view. Would that be helpful? QFT. I mean, if you want to do see QFT, go to the I forgot the name of the channel, but I'll write it down later in chat. So there's already dedicated channels on theoretical physics, on general relativity and quantum field theory. I'm not qualified to discuss that. This is a graduate physics topic, and I mean, right now it's just beyond me. And I love to learn about it, but once again, time management. There are other math thing I want to do. I wanted to thank you. I passed my interview for investment. Wow, that's crazy. That's crazy. Wow, thank you so much. But I mean, congratulations to you. This is awesome. Thank you so much. Oh, thank you so much, Felicino. Is that how I pronounce your name? Yeah, I would love to come to Europe, visit Europe one day. Thank you, and congratulations to you. Um, so, looking at what was listed there doesn't need algebra for those things. Exactly, exactly. You're right. You're right. Um, but once again, this is just my personal bias when it comes to training. Okay, I don't bias in the sense that I dislike them. Okay, guys. In case you guys didn't know, I started when my channel got hacked. I figured, you know what, screw it. I will just do whatever I want. And when a channel got hacked, I started a 2.0 channel where I started my first attempt on abstract algebra live. So that was what I did. But now that project has unfortunately taken a pause. Okay, I don't know when I will come back to it. I hope I will. It's not like I dislike those subjects. They don't click. That's not true, right? And I hope I get my points straight. Okay, right. So don't. I'm not a hater of abstract algebra. Um, it says my girlfriend is from Siberia and said you have good pronunciation. Oh, thank you very much. Spasiba. Spasiba to your girlfriend. Means thank you in Russian. So the Jewish exodus of Europe was very good for American. Exactly, exactly. This is a loss for Russia, like for the Soviet Union, and also Germany was. It also happened to Germany. Germany, well, before the Nazi took power, was a world center of mass research, and well, obviously they had to flee the country, including Koran. I think I made a video years ago. I mean, not years ago, about a year and a half ago, called "The Greatest Tragedy in German Mathematics," talking about that piece of history. And unfortunately, not everyone was able to escape. Guys, I'm sure you heard of the person called Hausdorff, Felix Hausdorff. Felix Hausdorff, well, he was one of the founders of modern topology, set theory, functional analysis, and measure theory, etc. Right. So Hausdorff space in topology was named after him. So yeah, he was Jewish, and life became difficult for him and family after the Kristallnacht. This was an infamous event during the 1930s. So yeah, so in the next year, he initiated efforts to immigrate to the U.S., but was unable to make arrangement to receive research fellowship. So on January 1942, Hausdorff, along with his wife and sister-in-law, died by suicide, rather than comply with the German orders to move to a concentration camp. Very dark. Okay, so basically, Nazis destroyed Göttingen. Göttingen was the center. Was perhaps it's not a not a so to say not a exaggeration to say Göttingen was the Harvard during the 1930s, but well, they lost it, and you know this is just what happened. So, okay, thank you. Do you have any lecture notes that come to mind if I don't find some? Well, I'll do my best. Okay, come to the Discord server. A lot of people have their uh, fantastic recommendations. The American also discriminate against Jews. Yeah, it's anti-Semitism was very much a universal thing in the West back then. Also in well, it's just mentioned in the Soviet Union, but also in America too. Yeah, so it sucked. It, well, I hope uh, I hope we as human beings have moved beyond that stage, but perhaps that's too optimistic. Still need to be very cautious about that. Okay. Do you know any great resources on QFT? I don't know. Perhaps David Doan. Like once again, my knowledge is pretty much non-existent, but at least I know David Doan. So if you like theoretical physics, your I think you will enjoy David Doan's lecture notes, quantum field theory. Yeah, they exist. Full lecture notes, QFT. Because my basic quantum is very rusty. I did took quantum when I was in uni, but I never used it for years. So, and the thing is, when I was in uni, I pretty much was like, well, as I described, I pretty much just did root memorization, mastered the practice problems, practice exams and stuff, and got a good grade, and felt good about myself, and didn't quite really what was really going on. So that's why I don't. I mean, I have the luxury now because I'm not in a university. I don't value university grades that much. I don't see a very good correlation between good grades and understanding anymore. At least for myself, I don't know, I can't say much about others, but I feel like even though I did good in a quantum course, I didn't really understand what was going on. Okay, that's just my self-confession. So if I wanted to say, come back to physics, I really wanted to say, use Shankar's quantum mechanics as my journey to learn the subject the right way. Okay. I mean, once again, this is not a criticism towards university. It was my poor usage of university resource. I figured, oh, if you just get the practice questions right and you get good grades, then you're above criticism. Like, there's nothing else for you to learn. I was totally wrong about it, right? So, yeah, if I come back to, say, quantum mechanics, I'll probably follow this one. This is an intro to quantum mechanics, and it is well regarded. So I'll probably follow this one if I come back and do more quantum stuff. But basically, if you're interested in QFT, go check out David Doan. Or just theoretical physics in general. David Doan, QFT. That'll be my recommendation, even though I never read it. Okay, I'm sorry. I usually don't recommend stuff that I never read because I figure that's unfair. But that's the only resource on QFT that's free that I know. Okay, I don't know what would be the canonical text in QFT. Okay, so question QFT. Okay, thanks. Hi, Andre. Thanks for joining the stream. You've always been very supportive of the channel. Thank you very much for it. Germany was on top of the world. Germany was very much a mathematical superpower. Kolmogorov published his foundational work on probability theory in German, not in Russian, not in English, not in French, in German, because Kolmogorov was answering one of the Hilbert's problem. So naturally, he out of probably out of the motivation to maximize international impact, he published in German. But due to subsequent political events in the Soviet Union, pretty much all Russian mathematicians published exclusively in Russian. Yeah, most Russian Jews also just went to Israel after USSR collapsed. That's true. If they have the means. Right? So could you recommend a good book or resources to start visualizing and learn linear algebra? I want to suggest it for some of my coworkers. Visual linear algebra. Visual linear algebra. I think Strang is a good resource. The thing is, to visualize linear algebra, it's perhaps the best practice to draw as many diagrams as possible. Okay, you don't need advanced visualization tools to visualize linear algebra. You just need to draw more diagrams. So to say, when you solve a linear system equation, try to draw the planes. Try to draw the planes. Let's say if you're solving a linear system with equation, you can always, I mean, if you have trouble with sketching, try to do it in decimals. A good book to start visualize and learn in algebra. I would just do Gilbert Strang, Felicino, Feliciano. Yeah, just use Gilbert Strang, and his lecture series on MIT OCW is fantastic. I'll probably sound like a broken record when it comes to recommending Gilbert Strang, but once again, you can't really go wrong with it. And there's so much readership of his viewership and readership of his book and lectures, so chances are you're more likely to get help when you get stuck. Right. Of course, you can always ask questions in the comment section on my Discord, but there's just so much readership and viewership followers of this course. Yeah, Gilbert Strang is always known for intuitive, no nonsense teaching. So yeah, go check out MIT OCW, linear algebra, Gilbert Strang linear algebra. Okay. So yeah, anti-Semitism definitely called a loss of it, but the economic situation of 90 was what finished up for good. Unfortunate. 90 was not the best time in the history of Russia or the post-Soviet space. Okay. Yeah, it's my belief that uni moves too quickly to condense content at expense of true understanding. I agree. But it has to do with the overall incentive structure. So if all the universities are doing this, right, and it would be difficult for others to follow, to do their own things and not be influenced by it, if that makes sense. If all the universities are doing this fashion, right, and they move too quickly to condense content and whatnot, they pretty much everybody have to do that. Anyway, so finally, my goodness, I'm finally caught up with chat, and it's 2 hours. Okay, let's do 2 hours of math. I mean, no digression, just pure, not pure math, but it's just pure applied math. Okay. Okay, guys, thank you very much for putting up with my commentaries and not doing actual math. I promise I'll be a good boy for the rest of the 2 hours and just do math. Okay. So, let's start with PDE. So, PDE, what is PDE? Are differential equations where the unknown function depends on two or more independent variables. Equation whose unknown look like this. u of x1 all the way to xn. So basically you have a multivariable function. Okay, that's it. And equations whose unknown is u of x1 all the way to xn and involves their partial derivatives. And involve partial derivatives of u. Okay, so it would be quite unhelpful to try to write down the general form of a PDE. There's little need for that. But let's just take a look at some example that arises from, I'll give two examples, one from traffic modeling, which also which is also equivalent to laws in fluid mechanics, as well as probability. So we'll do two examples. So let's take a look at this situation. The first model that we're going to establish is called one-dimensional conservation law. My bad. 1D conservation law. Conservation laws are, in general, a great way to derive PDEs in physics. So, imagine this is a road. Okay, imagine this is a road, and you have a bunch of cars. This is a highway, okay? On the road. 1D conservation law, and this is a particular example of it, called traffic flow. Traffic flow. So, of course, the traffic flow is a discrete phenomenon in reality. You got one car here, nothing between, and here's another car here. It's a discrete phenomenon. However, for the ease of mathematical analysis, we can treat this as a continuous phenomenon. We're going to model traffic by the density of car. That is the number of cars per unit length. Right, think about, say, a traffic jam. That will be high density in a particular section of a road, right? And let's think about let's think about the country road in the middle of the night. It will probably be very empty, so that will be low density. So the idea is to treat traffic flow as a one-dimensional scalar field, and that scalar field can evolve over time, right? Because the traffic flow in the rush hour is very different, say, during lunch hour. So it's a traffic flow, so we can model this as a function which depends on the position as well as time. So if it only depends on time, there would be no spatial modeling at all. Right? So if you just talk about, say, the traffic density at a particular point, then you ignore the spatial information. And let's say if you only have the spatial coordinate, then you can't really model evolution of the time, the traffic flow. So the traffic flow is modeled by this function, the rho of x and t. As I was saying, this is the density of the traffic, the number of cars per unit length. This is the density. And this is our main object of study, density of traffic at position x and time t. As I was saying, this means cars, number of cars per length. So this is our continuum model. Okay? It's an approximation of reality. Right? Just like in classical mechanics, we can treat fluid as a continuum, whereas, of course, in reality, fluids are made of discrete particles, atoms and whatnot. But on a scale, this is okay. On a scale. So if you don't look at individual cars too closely, this is still an okay model. So we need a few other quantities. Another one is Q of x. You can consider it as flux. This is a flux. So what does flux mean? Flux is the rate at which car passes through a particular position. Just think about you put a toll gate somewhere on the highway. So this is your x-axis. I forgot to label. This is your x-axis. Okay, and by the way, I should probably draw a illustration of the density field. So let's just say in certain portion of the highway, I was saying you have high density. So let's say density is high here, but is low here, for example. Let me just, this is a row. Okay, and I'm just going to copy this little car a few times to indicate over here you have a high density situation. So can you imagine what is going to happen? What can you intuitively, just based on your everyday sense, predict what is going to happen? So in the front section of the highway, you have high density. And based on our common sense, so these guys should be moving pretty slowly. Right? Because the gap, the gap between cars are smaller. A sane driver would slow down because it gives him or her less reaction time should something happen, right? So these guys are closely packed together, and as a result, they drive slowly. And over here, things are more sparse. Cars are more sparse, greater distance between them. So can you predict what is going to happen? Cars are going to line up. So we predict just intuitively that, say, if this pattern continues, then the high density region would move towards the left. Okay, so this is initial profile of the density distribution. And now the red one is what's after. What's after. So the cars that are so the high density region basically would have its tail gradually moving towards the left. So this is what we predict just by our common sense. Our mathematical model, if realistic at all, should be able to cover this sort of behavior. Right. Oh yeah. Sorry. I will promote the geometry channel if you guys on. Okay. I think it would be interesting to many people here. Or classical Euclidean geometry. Sorry, I forgot to promote it yesterday. So I will read the chat in a bit, but basically I want to continue introduce the notations, and after that I'll read chat and I'll do some more derivation. So this is Q of x and t, that's flux. Flux is, to define it precisely, that's the rate at which a car passes position. Position x at time t. Okay. Once again, this is car per unit time. Oh, sorry, this is car per time, not car per length. Okay. Density is car per length. This is car per time. Yeah. If you think about setting up a toll gate somewhere on the road, and you just measure, say, how many cars pass through that gate per minute. That would be the flux. Number of cars per time. Okay, that's the flux. And also the velocity of the traffic, v of x and t. velocity of the traffic. So it's like how fast cars are moving at position X. So yeah, Levy, if you don't mind, can you put the link of the geometry channel? It's called Olympia Geometry. They have very cool geometry problems, mostly from mathematical competition. Oh, hi, Steve. Steve, I read your comment on my Russian complex analysis video live stream. Yeah, thank you very, very much for joining the stream. And I appreciate your appreciation for French style mathematics. So we will see some of that down the road, which is different style compared to Russian style. So v of x and t is the velocity of traffic. Yeah, just how fast cars are driving at a particular position. So if you live in downtown Toronto, you're probably like this. Okay, very slow. If you're, let's say, living in say the prairies, what we call in the prairies, like these are the prairies are like the sparse fields in Alberta and Saskatchewan, perhaps also in Manitoba. It will be very sparse. Velocity of traffic at a particular time and space, at position x and time t. So these are the quantities the notations we denote, okay? So there should be a relation between them. So Q is rho times V, is density times velocity. That's Q. Think about why. So let's consider, say, a small time interval. So here, let's consider a small time interval, and small time interval with length delta t. Okay. And the cars in the road segment, say this is a road segment, a small piece of road. So this is x, and this is delta x, x minus delta x. So this is a small piece of road with length delta x near position x. So how many cars should pass through this position x during that time interval? Well, in the time interval delta t, the cars in the road segment of the length delta x, by the way, delta x should be v times delta t. Okay. The cars in the row segment of the length delta x equals v times delta t will pass position x. And the number of cars in this row segment would be rho times delta x, because number of cars in this number of cars in this little segment, by the definition of density is cars per length. So it would be rho times delta x. Right, so it's rho times delta x. And what would be the definition of Q? By definition of Q would be the number of cars divided by the delta x. So it would be rho times delta. Actually, not by delta x. Rho is car per time. You see, is rho delta x. That's the number of car over delta t. And delta x, as I said, is v delta t, so it's just rho v. So there's a relationship between Q and rho v. Q equals rho v. Okay, a lot of these derivations will be very similar to the one in fluid mechanics. And in fact, the whole traffic modeling was inspired by fluid mechanics. Okay, so there is that. You have this relation. And this is just pure definition. There's no physical assumption here. It's just pure definition based on these quantities. Yeah, exactly. Mass flow rate is density times volumetric flow rate. Exactly. Yeah. Okay. So yeah, now what we're doing. So let's now consider a non-small piece of highway. So this is what we're getting at. This is called the conservation of cars, which is really conservation of mass. Okay, but here mass is treated as the number of cars. Conservation of cars. Okay, so let's consider an interval, say x1 to x2. It doesn't have to be small. Okay, this is a fixed interval. These are fixed. So consider the road segment, which is an interval. Say x1 to x2. What would be the number of cars in there? At time t, the number of cars in the in this road segment is the integral from t0, not t0, but x1 to x2. Right? It's just integration of the 1D density, integral from x1 to x2, rho of x and t dt. Right. So that's the number of cars in this particular road segment at particular time t. Okay, so what would be the conservation law look like? The conservation law says the following. Assuming no cars enters or leave between x1 and x2. Okay, so assuming there's no ramp somewhere in the road, okay, no cars can join in there and no cars can leave. So that's the conservation law. Assuming that you have this condition, assuming no cars enters or leave between x1 and x2, which is a conservation law. So for that, what would be the rate of change of this quantity? The rate of change of the number of cars in the interval would be the rate at which car passes through x1 minus the rate at which car passes through x2. Here, x1 is in. At x1, the cars enter, traffic flows enter this segment, and at x2, the traffic flow exit this the segment. So the conservation law would be the rate at which. Okay, so we're writing a lot of words because I don't want to jump straight into solving PDEs, and this is modeling part. Okay, you have to understand what assumptions are baked into the model. Otherwise, you don't want to. I mean, we don't want to solve the wrong problem. Okay, and you want to understand the limitation as well as approximation intrinsic in the model. All models are wrong. Some are useful. Rate of change of numbers. Number of cars in interval x1, x2. Okay, this thing equals what? Equals the rate at which car passes through x1. This is in rate. Minus the out rate. Rate at which car passes x2. Okay, so there's that. How do we translate it into a differential equation? Symbolically. Well, the rate of change on the left-hand side would just be d over dt, integral of x1 to x2, rho of xt dt. Okay, so this is a left rate of change on the left hand side. On the right hand side, we just have the difference between the flux. So you get Q of x1 t minus Q of x2 and t. Flux, difference in the flux. In flux minus the out flux. So that's the conservation law in integral form. Let's box that. Okay, conservation law. This is integral form because there's an integral sign in there. And it discusses the conservation law over a finite region, not an infinitesimal region. Integral form. Okay, so how do we convert this into a differential equation, right? So we're going to assume a few things. First, we're going to assume you can differentiate under the integral sign. So the left-hand side, assuming you are able to do that, namely exchange the order between differentiation and integration, you get the integral from x1 to x2, partial derivative d over dt, rho. Oh, sorry, my bad. Here should be dx. What am I doing? Yeah, this should be dx, okay? Did I mess up? Oh, I messed up here. Sorry, guys. This should be dx. Did chat caught this? Because I haven't been reading chat, okay? I'm just doing this derivation. My bad. If chat has been screaming at me, oh, you idiot, you put a dx at the end, not dt. I apologize. Okay, so this is the left-hand side. Assuming you can do this, because you see I put a question mark here. In general, exchanging differentiation and integration is an intricate problem in analysis. Although physicists seem to be unbothered by this, they do this quite naturally, okay, as if this is always true. But once again, there are different standards of rigor and different priorities of rigor in different fields, which is totally okay. But to study or to justify this mathematically, you do need some intricate machinery, okay? In elementary calculus, you use something called the Leibniz rule, okay? Called the Leibniz rule. You can interchange the order of differentiation and integration. However, the assumption of Leibniz rule isn't always true, even in physically meaningful solutions. So to do this, you need measure theory. So in measure theory, there's this theorem called the dominated convergence theorem that allows you to interchange the order of differentiation and integration under fairly general condition. So I'm just hinting at where advanced analysis such as measure theory can be useful in PDEs. Okay. So on the left, we have this operation of interchanging differentiation integration, which assume is valid. Okay, this is nothing but assumption. Assume this is valid. Assume okay. On the right, we can use a little bit of a trickery. So the right-hand side, assuming Q is differentiable in X, we can write this in the form of a fundamental theorem of calculus. So this will be x1 to x2. Okay, t is treated as a constant on the right-hand side because you see time is constant. It hasn't changed. The variable x changes. So how do you write that? So you can think of this as first of all, let me write it this way. So this will be minus q of x2 minus q of x2 of t minus q of x1 and t quantity. All right, so here this will be minus integral from x1 to x2, and then you use the partial derivative. We're integrating the partial derivative, so dq over dx, partial derivative, x and t dx. This is by the fundamental theorem of calculus, FTC. Okay, once again, we assume that the function q is differentiable. To be able to do this, okay. Anyway, let's put these together. So therefore, putting these together, and now on the left and right you have two integrals, both from x1 to x2. You can bring them together. So you have x1 integrated to x2, d rho dt dx equals minus the integral x1 to x2 dq dx, okay, and therefore this is the integral from x1 to x2 d rho dt plus dq dx equals 0. Okay, so that's nice. And if we assume further that the integrand is continuous, then the integrand must be 0, since x1 and x2 is arbitrary. If you're integrating a continuous function and it's always 0 for every interval, then the integrand must be 0. Okay, so here we use another assumption, the continuity. Assuming this is 0, so assuming d rho dt plus dq dx is continuous everywhere, and since x1, x2 are arbitrary, the function has to be 0. So this way you manage to obtain a differential equation. You have d rho dt plus d rho dx to be 0 everywhere. And that's the partial differential equation. You see, this is an unknown function rho. Oh, sorry, here, my bad. It should be dq over dx, not d rho dx, dq over dx. Right. This is a partial differential equation. This is our first partial differential equation. This is known as the continuity equation, which really is a conservation law. So continuity equation refers to the conservation of a particular quantity. Here, we interpreted rho as the car density, right? But you can easily substitute that to say charge density, electrical charge density, mass density, or it can be probability density. So this is the continuity equation, because all these things are quote-unquote conserved. Why is that? Well, mass conserved, electricity conserved, these are physical observations. Probability conserved because the total probability is 1. Right. So here you have this equation called the continuity equation, which is really just a conservation law in differential form. Okay. Differential form in the sense that it is expressed in terms of derivatives, okay, not differential, the actual differential form in differential geometry. Okay. It's called the continuity equation. Okay, aka conservation law in differential form. Once again, this dual formalism is very common in physics in differential form. Okay, so for example, in the study of electrodynamics, Maxwell equation also has two forms. You have the integral version of the Maxwell equation and the differential form of the Maxwell equation. So physically they mean the same, although mathematically, as you can see, the differential form is more stringent. Mathematically, if let's say you want to take this equation literally, then you have extra assumption baked in. Right? You assume you can differentiate under the integral sign, assume fundamental theorem of calculus works for the right-hand side, and we're assuming that the combined integrand is continuous. So even though physically they say it's the same thing, mathematically speaking, differential equations are more stringent. You're introducing extra assumption. But is this actually always true? Let's say the mathematical assumption we introduced along the way, is it always actually true? Not quite. Not quite. Think about it. Think about what really happens in a traffic jam. what really happens in a traffic jam is that you have a bunch of cars basically moving at turtle speed, practically at a stop, practically stop. And now you have cars moving behind it. So based on our everyday knowledge that at every instance, the density function experiences a jump. So you have high density here, say. Eventually this will develop into something like this. Yeah, based on where this is going, okay, high density of in the front and low density at the back. Eventually this will create a traffic jam. And a traffic jam mathematically is a jump. And we will call this a shock wave. We will call this a shock wave. So physically, a discontinuous function would make sense. A discontinuous function, let's say a jump function, a row that has a jump in x, is physically meaningful. But here, by assuming differentiability, we're actually ignoring that particular aspect of physics. And this is important because we don't just do this modeling for the traffic flow for fun, right? We wish to predict and control traffic congestion. So this is very much the central object of study and is not even included in the classical equation. So this is why the notion of weak solution needs to be introduced. So let's say if the function is non-differentiable, not even continuous, how this is interpreted. Right. Okay, so I finished this derivation and I will look at chat. What does chat say? Yeah, so where did I? Yeah, linear algebra, I think you're moving too quickly is good. The idea is you understand everything during the course paradoxically holds you back. I guess the nice thing about math is that, and I think it's unavoidable, is that you reach a certain level of understanding on a topic, and then you move on to the next topic, but then you come back to the original topics. And this way you get a completely new level of understanding. You rarely learn, say, a topic super deeply in the first attempt. You get a familiarity with one, and then you move on to more advanced topic, and then you come back, provided you come back. The problem is a lot of us don't get the opportunity to come back. Right? It takes time to revisit fundamentals. So how many people say, let's say, they take calculus from Stewart, and then like all of them, okay, from single variable to multivariable all the way to vector calculus from Stewart, and did differential equations, PDEs, and all those quote-unquote more advanced topic, which justifiably so, and then come back to calculus and see what they missed. I mean, I don't know if a great number of people actually do that. If so, that would be great. Right? So sometimes you can't afford, say, in day one, and on planet pedant, okay, not planet Earth, on planet pedant, right? You prove every theorem in calculus in the standard of real analysis before you move on to application. I don't think that's feasible. I'm just saying, like, it's okay to get your first understanding, a passing familiarity, a working knowledge of a subject, and then come back. In fact, that was my philosophy on much of the content on the channel. Right? My stochastic series is, I mean, in the making. Right now we're on Ito's lemma. So my stochastic series is entirely heuristic. Right? I'm not saying measure series is useless, but it shouldn't stop you from not knowing measure series. Should not stop you from gaining a working knowledge of a subject, and then you have more advanced analysis filled up, and you can revisit the topic from entirely new perspective. It's totally okay. Okay, Ego, I'm not a professor. Okay, but thank you. I think it would be help to divide stream by content like math stream, textbook discussion stream, not answering textbook questions during strict math and redirecting them. Yeah, that would be helpful. That's a good idea. That's a good idea. The thing is, I mean, this is meant to be a first introduction to PDE. So I think this was very much an anomaly. I typically don't spend a lot of time discussing pros and cons of various textbooks on these lives. Okay, typically it would be just, hi guys, welcome to the measure theory live stream. Last time we were on measurable functions, and this is the definition of a real sigma algebra, and blah blah blah. Okay, so I think I'm okay, forgive me if I'm cutting myself some slack for this stream. Yeah, so yes, this is not university lecture, right? This is more a seminar style. So reminds me of Poisson arrival time. Yes, yes, that would be a actually, you know what? You read my mind. My goodness. Actually, my next example would be a stochastic process. Not for traffic flow, okay? Not for traffic flow, but would be stochastic process. And it's related to Poisson arrival rate. Okay, thank you very much for bringing it up. Levi, I will actually, you know what? I'll do it right now. My goodness, I should do it right now, and I'll make a separate post, okay? Because not everyone reads live stream chat. I'll do it in a separate post. So there's this channel which I discovered yesterday thanks to Levi, which is called hang on, what's that called? Olympia Geometry. Yes, Olympia Geometry. Very valuable stuff. Olympia geometry. Just amazing, like how complicated Euclidean geometry problem can be. Olympia geometry. Even though we have all these advanced subjects in geometry, you know, algebraic geometry, differential geometry, convex geometry, and what? Information geometry coming up next week. Okay, so Euclidean geometry is still a treasure trove. So why doesn't load? Yeah, so this one, Olympia Geometry Club, maybe I could just find the share link. Yeah, I'll paste it in chat. Great stuff, great stuff. All right, so Abraham Lincoln reportedly studied the first 6 books of Euclid's geometry to practice his reasoning skill, because he was a lawyer and later a politician. So I wish more politicians do that, man. Perhaps this is why we don't get Lincolns anymore. They stop studying geometry. Well, maybe Lincoln was an anomaly anyway. You don't get a guy like Lincoln in a 1,000 years, perhaps. That's a shame. Okay. Anyway, so continuing with chat. So help me secure an A. Thank you very much. Thank you very much. Did I do that? I mean, I'm not a professor, but anyway, you have secured an A. Wow, that's crazy. I don't know what I did, but congratulations to you. Thank you very much. I mean, for finding my stuff helpful, I guess. I try to be helpful. Okay. Yay, made it to the PDE stream. Thank you, Speed and Power, for joining the stream. Engineers be like dq over dx equals 1 implies dq equals dx. Yeah, I mean, actually, I do that a lot of time as well. There's nothing wrong with that. There's nothing wrong. I mean, dq and dx can be mathematically defined. Ah, yes, solution. Yeah, it really depends, right? It really depends. Once again, I was saying, rigor isn't just mathematical rigor. The notion of rigor is multifaceted, and it's totally okay for different professions to prioritize different rigor. Mathematicians like to prioritize, pure mathematicians like to prioritize formal rigor. Okay, whether your assumptions are unambiguously stated, are there internal contradictions between the axioms? Do the conclusions actually follow from the premise? Right? These are formal rigor. These are important, right? Especially for a mathematician, for a pure mathematician, where you don't have where you don't, let's say, judge your so to say, your results based on experimental data. There's no such thing in mathematics. So everything has to conform to strict formal logic and formal rigor. That's what I say. But for applied mathematicians and engineers, applied scientists in general, modeling rigor is equally, if not more important, right? Like if you solve the wrong mathematical problem, mathematically, if you solve the wrong problem, in a mathematically meticulous way, it will still do you no good in reality, right? So is there this notion called the modeling rigor. It's also important. So it's okay at certain situation to ignore or down, or so to say, to de-emphasize, not ignore, but de-emphasize formal rigor. Yeah, probability dense. Hello, quantum mechanics. Exactly. In quantum mechanics, you have the conservation of probability, and in quantum mechanics, we talk about probability flux. I mean, my quantum is very rusty, but I vaguely remember those notions. Yeah. Where's the problem taken from? It's from my own notes, but it is also in Haberman's book, Wendelin. This part of the derivation is very much in Haberman's book. Actually, you know what? I'll just show you the content in the Haberman's book in the list, in the content list. Okay, so you know which to look for, because the Haberman's book is pretty big. I didn't start from the start. I didn't start from the beginning of the book. That's what I mean, because I figured I should do first order first before moving on to second order. Okay, so yeah, let me just check out the content list here. It's actually in the later part of the book, even though you don't need the stuff that's earlier. Actually, it's in a pretty late part of the book. I don't know why he put it at the end, but basically, yeah, it's this chapter, the method of characteristics of linear and quasi-linear wave equation, and I'm doing this one, the traffic flow, 12.6.2. traffic flow. So I would like to do modelings first and then discuss solutions later. So yeah, some people like to introduce, okay, this is a mathematical form of the first order PDE, and then let's look at the solution method, and then here's an application. Okay, I like to do things in the, I wouldn't say completely opposite way, but I like to put the reality first, because I feel like I need to give a reason why you should give a damn about this stuff before you decide to spend your time on it, not introducing application as some kind of afterthought. Now, this is what drives PDE research, fundamentally speaking. So yeah, this is the derivation of the wave equation. Do we have more chat messages? Yeah, that'll be it. I think that's, I'm all caught up with chat. Let's continue. So we have this differential equation. However, there's still something missing here. Because remember, this is just one equation, and we have two unknowns. Rho and Q are both unknown. And even if you substitute Q equals rho V, right? Q equals rho V into the equation. Since Q equals rho V, we have d rho over dt plus d bracket rho V over dx. Even if you do that, there is still an unknown V in the equation. Yeah, I love PDE. Yeah, you should. This is amazing stuff. The power of mathematics is, this is the quintessential example of power of mathematics, of understanding nature and society. Okay, so d rho over dt plus d of rho v over dx. There are two unknowns here. That's my point. So how do you resolve that? So you need to introduce a so-called what we call a constitutive relation. This is what physicists like to call it, right? Steve, you're the physicist. Did I use the term correctly? A constitutive relation. So you need a constitutive relation between rho and v. So here, let me go right this way. Still, there are two unknowns. This is not enough to solve the PDE. This is underdetermined. Two unknowns, uv, rho v, should be related. Okay, so this leads to an underdetermined model. So we need to introduce some assumption here. So far, the assumptions introduced are, I wouldn't call it natural, but more fundamental. You have the conservation law. as well as certain regularity assumptions. So here, these are regularity assumptions. Assume differentiation under integration, okay, this is regularity condition. Assuming fundamental theorem of calculus work, this is another regularity assumption. And also you assume the partial derivative sum is continuous, okay? So this is also a regularity condition. Mathematical in its nature. But here, the system is... Yeah, guys, can you hear me now? Yeah, the stream froze because of crappy internet connection. I'm so sorry, guys. Okay, guys, can you hear me now? I think, yeah, a couple of people left because of the shitty, sorry, I shouldn't use bad language, but just terrible connection. That's okay. That's okay. I mean, I might have to just upgrade my plan for the internet. Okay, hopefully I'm back. Okay, so I was saying that you need a constitutive relation between rho and v, but how do we establish that? Well, think about how drivers adjust their speed according to traffic condition, right? So if you have a density region, if you have a high density region, then you're likely to drive slowly, because high density means smaller gaps between cars, which leaves you with a smaller reaction time, and for that reason you drive slowly. So there should be, so intuitively, constitutive relation is basically rho as a function of v, or v as a function of rho. Both are okay. Okay, so rho and v should be related. The denser the traffic, the slower the speed. Because of reaction time. Lower, smaller separation between cars means smaller distance between car, means lower reaction time in case of emergency. So you drive slowly. It's just common sense. Drive slower, right? So that's the idea. And from that intuition, we can assume, just as a simple model, okay, assume for simplicity that rho and v has a linear relationship. Okay, so here, let's say this is v as a function of rho. So v as a function of rho is perhaps more appropriate, right? The driver adjusts his or her speed according to traffic density. So this is rho, this is v. Imagine if there's no car on the road. If rho equals 0, and you would have a maximum speed, Vm. Let's say this is the speed permitted by law. Okay, I know in Europe sometimes they say in Germany they don't have the upper limit, which sounds insane to us in North America. But let's just say this is the maximum speed of either permitted by law or physical restriction. Okay, so that's the maximum speed. Assuming the road is entirely yours, so you can drive at max speed. This is Vm. And let's say you have a max density. This is a max density. At max density, the traffic just grinds to a halt. So cars is now bumper to bumper. And we just assume there's a linear relationship between them. Just linearly interpolate the two extreme points. Okay. So here, this point is open highway. The vertical intercept is open highway. And here, this is complete traffic jam. Okay, yeah, this is traffic, the worst traffic jam imaginable. So these are the two extreme scenarios. Let's just interpolate them linearly, okay? So we can write down the equation. So there will be V over Vm, because assuming a straight line. The intercept form of the straight line will be V over Vm plus rho over rho m equals 1. So let's solve for V in terms of rho. Here. Therefore, V as a function of rho would be Vm times 1 minus rho over rho m. There you go. This is V rho. And now substitute this into the continuity equation. This is a constitutive relation. In physics, constitutive relation typically refers to, say, the relation between two physical quantities due to properties of material. Okay, like how, for example, the Ohm's law, V equals R times I, is a constitutive relation. So the two physical quantities V and R are related through property of material R. Okay, so I'm just using a vague analogy here. And also a relation between, say, Q and M. Q equals Cm dt, dq equals Cm dt. This is also a constitutive relation. So yeah, it's related to the object. Q is heat, dt is the increment of d big T, okay? Increment in temperature, C and M. C together is the heat capacity. To introduce this sort of constitutive relation to relate physical variables. So here we relate V and rho just based on traffic behavior, driving behavior. All right, so together, so yeah, I guess why not assume P V equals 1 over V? That also works. Rho V equals 1 over V. That also works. The point is not the linear form, but rather a decreasing function. I guess perhaps 1 over V, the biggest problem with 1 over V, okay, if let's say rho is 1 over V, if rho is 1 over V and V is 1 over rho, what happens when the traffic grinds to a halt? You don't have infinite density, do you? What happens when the traffic grinds to a halt? In this definition, you have rho equals infinity, which is also problematic, right? Instead, we assume there is a max density. If you just park the cars on the highway from bumper to bumper, you would still have a finite density, right? So this is, I think, the biggest problem with this inverse relation. I mean, it is totally possible to have a nonlinear decreasing equation, but the overall idea is decreasing. Is the monotone decreasing relation between density and speed? That's the main point. Okay, so yeah, a great question. Okay, these are modeling assumptions that we often need to question and modify. A lot of mathematics, applied mathematics in particular, was done this way. How do you change one condition and see what new reality it captures and that sort of thing? So, and now let's just stitch everything together. So together what we have here. So together we have this relation, which is, so dq, we need to evaluate the dq over dx, right? dq over dx, that's d over d of rho v over dx. Let's evaluate that. So v is now in terms of rho, so plug that in. D over dx of Vm rho minus rho squared over rho m. Okay, remember rho is a function of x, so here because of rho squared you need to use the the chain rule. So Vm times d rho over dx minus 2 rho over rho m times d rho over dx. So d rho dx can be factored, so you get Vm 1 minus 2 rho over rho m times d rho dx. Okay, so if we not assume this particular form of v in terms of rho, in general, if you just assume a general relationship between v and rho, dq over dx would be still d of rho v over dx. Differentiate that, you would have, still we assume there's a relation between v and rho. Okay, v is a single variable function of rho, so that way you get dq over dx, use the product rule, d rho dx v plus rho dv dx. And lastly, dv dx can be written as a product rule, a chain rule, so rho times dv d rho. So v is a single variable function of rho, so that's just v prime of rho times d rho dx. And then factor this, you get v plus rho times v prime rho. V plus rho times v prime rho, and then d rho dx. That would be the general formula for dq dx. But the point is, now we have a PDE for a single function. So assuming this, assuming the previous form, okay, assuming the previous form, that's v rho equals vm times 1 minus rho over rho m, linear relationship between v and rho, and you get this dE. So therefore you get d rho over dt plus c times 1 minus 2 rho over rho m times d rho dx equals 0. So this is our traffic flow PDE. The traffic flow PDE, okay? So, and now we can introduce some terminology. This is what we call a nonlinear PDE. Why is it nonlinear? Because the coefficient of the partial derivatives depend on the unknown. Yes, at some point experimental data is needed, definitely, right? So far we're just theory crafting, right? Which, I mean, seems intuitive, right? But at some point you have to support your experimental data to you have to support the model with experimental data, exactly. Which is a different problem, right? So you gotta fit the model, which includes, I mean, fitting the model is essentially optimization problem, least squares and whatever. So, yeah, that's the model. And I think now it is time for us to introduce some terminology. So this is a nonlinear PDE because we lack the part of backing up the model with experiment. Yeah, so this is difficult, right? So you need dedicated data set. Hopefully this will be more widely available in the age of AI, right? So hopefully, but still, this is still, I think theoretical science do have their place. Theoretical science do have their place, and of course, all theory should be judged based on their predictability. But sometimes theory crafting itself, on its own, is still valuable, even though, say, its fundamental assumptions are hard to justify, but its consequences must be tested against reality. Okay, so I'm just gonna introduce some terminologies here. This is an example, traffic flow PDE. This is an example of first order, because only first order partial derivatives are present. First order quasi-linear. So this is non-linear because the coefficients of the partial derivatives the coefficients of partial derivatives involves the unknown function itself. The rho itself appears in the coefficient, quasi-linear. And this will have fundamental consequence in the nature of the solution. Okay, so it is essential that this model is nonlinear. Linearity, perhaps not in this stream, but later on as we will see, in the traffic flow PDE, if you only assume linearity, you cannot do it much meaningful modeling. So you need this to be genuinely nonlinear. You can't always linearize your way. So this is a quasi-linear, so it's not linear, but it's quasi-linear in the sense that the derivatives themselves, the partial derivatives themselves, only appears as linear factors, if that makes sense. So this is called quasi-linear. We'll write down the general form in a bit. So this is first order quasi-linear type PDE. Okay, so here, let's give the general form of a first order linear PDE. Definition. Definition. So if you have, say, u of x and y, u of x and y is unknown function. So the general form of a linear first order PDE would look like this. Okay, so hold on a second. Yeah, it would be like this. So you have coefficients a of x and y, which potentially depend on x and y, but not u. Okay, a of x and y times du dx plus b of x and y du dy equals c of x and y. That's the general form of a linear first order PDE. Okay. Okay. And what would be a quasi-linear? The general form of quasi-linear first order PDE would be as follows. So the coefficients a, b, and c can now depend on u. Okay, while the rest of the format remains. So it would be a of x, y, and u times du dx plus b of x, y, and u times du dy. And then equals c of x, y, and u. So that would be the general form of first order linear, quasi-linear. Actually, it would be linear first order PDE or quasi-linear first order PDE. That's the general form. That's why the traffic flow PDE is an example of quasi-linear PDE. Okay, and typically for the traffic flow problem, we wish to solve the PDE by given an initial condition. That is to say, suppose we know the initial profile of the car. So if we know initially the profile of the density, given rho of x and 0, we know what the distribution of cars looks like at time t equals 0. We wish to describe its evolution. Okay, so let me put that down. Right, so that's the general problem we wish to solve. Okay, so here. Also, typically given the initial condition. This is called an initial value problem. Just like initial value problem in ordinary differential equation, like in solving the equation of motion, like from Newton's in the Newton's law, right? You have the initial position, initial velocity, you have the Newton's second law, like in the harmonic oscillator, you want to predict the trajectory, which is essentially the problem of exterior ballistics. You have the Newton's law, although very complicated. Right. and then you're given initial velocity, initial position, predict the projectile's trajectory. So that's the initial problem. Here in PDE, initial value problem is still very important. Typically also given rho of x of 0. Let's just call that phi of x. This is given. The initial profile is given. We wish to describe, analyze its evolution. Okay. So as you can see, this is a very important class of PDE, simply because of the conservation law, the scalar continuity equation conservation law is first order, right? And here the constitutive relation is also it involves no derivative, right? So the constitutive relation Vn rho is only is a deterministic function, so that's given. There's no extra derivative involved, so the PDE says first order. However, if you interpret, say, interpret rho not as car density, but as, say, energy density. So now imagine you're considering the problem of heat transfer in one dimension. So you can swap rho to energy density. And for that, you would need different constitutive relations. So what end up happening is, I'm just only hinting it, okay, I'm not going to give the derivation for heat equation because this is second order. The idea is the conservation law would still be very much the same. What end up changed is the constitutive relation in heat transfer, known as the Fourier's law. Fourier's law basically says the flux is in the direction of the temperature gradient. Remember, from multivariable calculus, gradient gives you the steepest direction of ascent. Fourier's law says the direction in which temperature decreases the fastest is where the heat flux is going. And you put that together, you suddenly have the heat equation. Very much in the same spirit we derived the conservation law for cars. Okay, so I'm just mentioning that in passing. And so we've seen one example and seen a formal definition. Let's give another example to see how PD arises in diverse field, which in my opinion is perhaps one of the most fascinating aspects of PDE. Okay. This is to showcase why this field is worth studying. Okay. Okay. So, wow, the views has been very consistent for this one. I think this will be a great idea for the channel. Perhaps an evergreen series on the channel. This is crazy. We're doing hardcore math and there's still 31 people watching. Love it. Thank you guys so much. So I'm not going to I'm going to do another example model 2, and this is a stochastic process called continuous time birth and death process. Continuous time birth and death process, as you can probably tell from the name, it is originally a population dynamics model. Birth and death process, BD process. This is a stochastic process. Okay, I'm not sure if today I will have time to actually cover the solution method, but I will definitely finish covering this particular example. Continuous time birth and death process is a stochastic process. Okay. Any book for probability and stats, go check out U of T, Michael Evans. Okay, let me just paste that real quick. This is the extremely common question on the channel. U of T, Mike Evans, yeah. Okay. Free book, completely free from the beginning. Full solution manual available. Okay. We stream, currently we're on chapter 6. Tonight we'll do chapter 6. So basically I aim to cover chapter 6, 7, and 9. 6, 7, and 8. Anyway, so coming back to continuous time birth and death process. So how does this work? So the idea is, at each time you can okay, let me just write it this way. So the process is denoted as x of t. Is x of t. X of t is a function of t, obviously. So it can increase or decrease by exactly 1 unit. So think about x of t as the number of individuals in a population. The word individual can be interpreted in different ways. Okay, it doesn't have to be human individuals in a population. It can be molecules in a chemical reaction. It can be, say, the number, the size of the current length of a waiting list, right? That kind of thing. It doesn't have to be a population in a biological species, even though it's one of the most common application of the birth and death process. Population. The number of individuals in the population. So imagine how this is going. So let's say initially there is n naught, which is an integer. Okay, this takes values in 0, 1, 2, all the way to infinity. Okay, so this is x of t is a non-negative integer valued stochastic process whose parameter is a real number. Okay, so you can imagine, so it stays constant at a time, and then it goes up by 1. So in birth and death process, you can only change x of t by 1 unit at a time. It either goes up by 1 or goes down by 1. Okay, so here, let's say you should keep going up. The waiting time between the transition is random. There's a random waiting time. Here, these are all random times, okay? Otherwise, it will be a deterministic function. If you know all the transition time, and you know whether at that time the process goes up and down, the process is completely determined. This is a random process, so you don't know when the transition happens, and you don't know whether the transition is up or down. So, okay, like this. So this is a sample pass of the birth and death process. You can go up or down at each transition. At each instance of transition, it goes up or down. No other option. And the switching time is also random. So that's the idea of a birth and death process. So let's write down things formally. X of t is the number of individuals in a population and takes non-negative integer value. So we're going to introduce some parameters. So the parameters, so you have the functions or the parameters to describe this birth and death process. The functions involve the birth rate and the death rate. So let's say the birth, the so-called birth. Birth means x go from n to n plus 1. A birth occurs at rate lambda n. This is our notation for the birth rate. Lambda n. Lambda n is a sequence, okay? It's a sequence of non-negative integers. The birth occurs at a rate lambda n, moves the process from n to n plus 1. Okay, so let's say the current value of the population is n. It goes from n to n plus 1 at a rate of n plus 1. At a rate of n plus 1. Yeah, sorry, at a rate of lambda n. What am I talking about? So if the current rate is n, if the current state is n, currently, okay, at time t, the population size is n, then it moves to n plus 1 with a rate of lambda n. The meaning of rate will be explained in a second. Okay, this is interpreted probabilistically. Okay, we'll explain this in a second. So basically here we're just defining the functions, the birth rate and the death rate, a death, so-called death. You can imagine what death is, right? Death means the process goes down by 1 unit. A death occurs at rate mu n, moves the process from n to n minus 1. So these are two functions. You have the birth rate and the death rate. Let me highlight those. So these are the fundamental parameters, which are really functions of n that describes the process. Okay, no other transition possible. Can only go up or down by 1 unit. And we can illustrate it with a diagram. No other transition possible. So here we can draw the diagram like this. So 0, 1, these are states of the stochastic process. So it's a continuous time Markov chain. 0, 1, 2, 3, etc. Okay, so you have 0 to 1, that's lambda naught. 1 to 2, lambda 1. 2 to 3 is lambda 2, and so on. Okay, still, I have not explained, okay, how do you calculate things with these functions? Okay, but this is just a diagrammatical illustration. Okay, and then 0 from 1, that's a death, mu 1, with rate mu 1. Okay, 2 to 1 is also a death with rate mu 2. 3 to 2 is a death with rate mu 3. So these are general sequences. Okay, and so on. So this is a transition diagram. You see that a lot in the theory of Markov process. So now we need to explain the meaning of rate. What do you mean by that? The meaning of rate is as follows. So suppose the current state is n. Suppose the current state is n. So what happens next? So what happens in the next time interval? So current state, let's call it xt. X of t is n. Current state x of t equals n. So we want to investigate the possibility of the process after a short time instance. So consider a small delta t. Consider a small delta t, okay, positive. We want to investigate the state at t plus delta t. So this is, we call the probability of birth. Probability of birth means the probability of x of t plus delta t equals n plus 1, given that at x of t, at time t, okay, is equals n. So that means in the small time interval with length delta t, a birth happens. It goes from n to n plus 1. Okay, so sometimes we also write this as p of n to n plus 1. Okay, of course this is a ambiguous expression. What we really mean is this. Okay, this is the full expression, p birth. Okay, and as we said, birth is described by the birth rate. This is a rate at which a birth occurs. So that will be lambda n times delta t. So that's the meaning of lambda n. Okay. See below. That's the meaning of the rate. Lambda n times delta t, and then plus higher order term, little o of delta t. So this is what happens in a small time interval. And now, similarly, you can define the death rate. So p of n to n minus 1, which we also call probability of death, will be p of, you can probably already write down the exact definition yourself, the t plus delta t equals n minus 1. And then x of t is n. So that would be mu n times delta t. Somebody mentioned earlier that this is just like a Poisson arrival rate. Exactly, because in a Poisson situation, there's no death. Right? Poisson arrival rate is used for, say, modeling football matches and other things. Well, World Cup was just over, but basically you can model the score, the score in a football match, or if you're American soccer match, as a Poisson arrival process. So in that situation, all the lambdas are constant. In the most basic situation, the lambdas are all constant, and the mu is 0. There's no, because score cannot go down. So this is basically the two possibilities. Of course, there's also nothing happens. It is possible to have no change at all during the same time interval. So there will be no change. So p from n to n, which is p, no change, which is the probability of x of t plus delta t equals little n, given that x of t is also n. So nothing changes. The probability that nothing changes is just, well, 1 minus lambda n delta t minus the two possibilities. 1 minus lambda n delta t minus mu n delta t, and then plus higher order of delta t. Okay, there's that. And lastly, 2 or more jumps. Probability of 2 or more jumps is negligible. So during a small time interval, provided the time interval is small enough, the probability of 2 jumps, 2 or more jumps, is negligible. Okay, this is just O delta t, little o delta t, all right? So this is the meaning of rate. So you can think of this as the axioms for the continuous time birth and death process. Okay, and so we can describe this. We can describe this as what we call a system of differential equations. We call this a system of differential equations. So we have the forward equation, also known as the Kolmogorov forward equation, to describe the evolution of probability. Okay, so let's write that. So here you have what we call the forward equation, also known as Kolmogorov's forward equation. And I believe I will introduce the PDE version of forward equations. Here we only have an ODE. Okay, we only have a system of ODE for the forward equation in the continuous state. So if, let's say, if x can take continuous values, here x can only take discrete value. If x can take a continuous value, like in a stochastic differential equation, then the probability evolved according to a PDE. Okay, but here we're not there yet. Okay, I don't want to introduce stochastic calculus in this particular life. I just wanted to describe the probability mass function. So we wanted to describe Pn of t. Let Pn of t to be the probability of xt of n. Xt equals n. right? So that's the PMF, probability mass function of the random variable x sub t. So how does that behave? Well, it just behaves according to a differential equation. So by the law of total probability, which I will skip for now. Okay, so from these assumptions, you can easily derive the forward equation, which is dPn over dt. dPn over dt equals lambda m minus 1 times Pm minus 1. We actually give a derivation that is very similar to this one in a video I posted about a month ago called Brownian motion and heat equation. So I'm just going to give out the ODE here. Okay, because I'm running a little bit low on time, I want to finish deriving a PDE. So I'm going to take this as given, okay, forward equation. This tells us how the probability mass function evolves in time. Okay, so the probability mass function evolves in time is intuitive, right? Let's imagine if you know the initial state. If you know the initial state n0 for sure, then the probability mass function of x0, the random variable x0, is highly concentrated because you know the value x n0 for sure. But after that, the distribution becomes more widespread. As time evolves, the possibility for xn, the possibility for xt becomes greater. So it becomes less and less certain. So the probability mass function evolves in time. So that's the differential equation, dPn over dt. That's the ordinary differential equation. However, that's a system. Remember, n can be 0, 1, all the way to infinity. And this is true for n greater or equal to 1. For n equals 0, dp0 over dt, the differential equation is as follows. Okay, so deriving this would lead us too far into the probability theory, so I'm going to skip this for now because that's not the focus of this stream. So hopefully we can take this as granted and move on with the derivation of the PDE. Okay, this is n equals 0. Forward equation, backward equation deserve their separate treatment in stochastic processes. Okay, so can you guys hear the sound very clearly? Yeah, guys, I think I'm going to answer a few live questions in chat. So here, there's not many questions, but basically Armin, thank you very much for helping me with my Russian. Do you have any videos for those who are revising school level? Yes, exactly. Go check out JC Practice Math. Yeah, so did I link it earlier? Perhaps I should do that again. JC Practice Math. Yeah, this one. So go check out his stuff. He has dedicated series, in particular this one, Math Can Be a Hobby. Click here. You see it, school level math. And it's an ongoing series, so go check him out. And if you're ahead of him, okay, let's say if you're ahead of him, go check out the book he's following by Serge Lang, Basic Mathematics. It's a sick book. Okay, it covers not just arithmetic, but also geometry, trigonometry, things like that. Basic math. This is school level math. Okay, let me put it in chat. Okay. Okay, cool, awesome. So Wendell asked, natural numbers do not neglect. Natural numbers do not include 0. Okay, this is the official ideology of analyst. Okay, so and which I firmly subscribe to. So natural numbers do not include 0. I mean, just kidding. Like, this is a meaningless debate. It's just a matter of convention. The whole point about natural numbers is that there is a base case for induction. So natural numbers axiomatically is defined using an induction. And for any induction, you need a base case. Sometimes you choose 0, sometimes you choose 1. And that's it, right? There's no mathematically interesting discussion to have. It's just different tradition. I am pretty sure Wendelin is joking. In analysis, most of the authors use 1 as the first natural number, which I subscribe to. I found natural to me at least. So funny thing is, when I do coding in Python, I often make this mistake of treating the indices starting from, or the labels, okay? The NumPy array index start from 1. And because I program in a mix of R and Python, R start from 1, and Python start from 0. So I often, even to this day, after a decade, I still find them confusing. Like 1 start from 0, 1 start. So I guess it's fair to say that computer scientists like to start natural number with 0. Okay. Creating life from nothing. Yeah, this sounds no problem. Okay, cool, awesome. No worries. Yeah, go check out the book called Basic Mathematics by Serge Lang. Basic Mathematics, also book. I think it's very accessible to high school level and as well as people who are revisiting mathematics. Basic Mathematics by Serge Lang. I wish I can, because I don't know many intro to math or school level math in Russian, or at least, or maybe translate will be even better. I mean, for my current level of Russian, but I wonder what kind of material, perhaps material will be similar, but the approaches Russian Soviet Union take when it comes to basic mathematics. Do they emphasize a lot of abstraction, proof skill, or is it mostly computational? How do they do things there? Okay, I'll be interested in those. But this is Serge Lang. Serge Lang, famous mathematician, research level. He published a lot of research level book. This is his approach to teaching basic mathematics. So what should I learn what kind of math give you those formulas? So you mean this formula? Here, this one, the forward equation. Sorry, I could not derive this in this stream because I really want to get into the PDE, because right now the purpose is PDE, right? I introduced the background knowledge. But if you want to see forward equation, how forward equation is derived, check out Sheldon Ross. Okay, this is my reference. Sheldon Ross's book, Probability Model. Introduction to Probability Model. So, yeah, there you go. Sheldon Ross, Introduction to Probability Models. This is an excellent introduction to stochastic process. Wow, right now it's in its 10th edition. It's an insanely popular book, actually. The Introduction to Probability Model, it derives the forward equation. Now, Kolmogorov forward equation. Let me put it here. Like those in... Shady, you asked that a few times already, right? Because the thing is, I'm not a professional trader or anything. Those in algorithmic trading, actually, I have to do my homework on that. Sorry, I cannot answer that question right now. Okay, but basically, my reference for what I just stated, the Kolmogorov formal equation, is from Sheldon Ross' Introduction to Probability Model. Here. S. Ross, Intro to Probability Model. So it covers topics like Markov chain and stuff. And just Ross's text on probability is worth checking out in general. Another great one would be simulation, his text on Monte Carlo simulation, on probability model. We'll probably do lives on Monte Carlo simulation in some future lives or videos. Okay, and even for this kind of more technology-heavy fields, technology-heavy field like numerical methods, simulation, and machine learning. I mean, I don't have any of those live session. right now. I don't have yet any live session on that. But when we do that, the format will be pretty much the same. Just focusing on the fundamentals, derive everything from scratch. And if you know the fundamental, you should be able to code it yourself. Okay, and whichever calculation we do during this live will be manual. Just zero distraction, pure logic. That's my philosophy. An algorithm should live in one's mind before one touches its software form. Okay, so that's the forward equation, and what do we want to do with it? Okay, so what do we want to do with the forward equation? So we can derive a let's look at a simple example. Okay, a special case. Special case. Special case. This is called Malthus growth. Okay. How do you spell Malthus again? Malthus. Malthus was a British economist. Malthus / linear PD process. Well, actually, Malthus did not invent the stochastic version, but he did invent the deterministic version. The stochastic or linear Bessel process is really just a stochastic analog for Malthus' original model. In the special case, you have the mu lambda n equals n times lambda, okay, where lambda is a constant, and mu n is n times mu. So we can interpret the constant lambda and mu as the birth and death rate of individuals, So you can interpret the single lambda, okay, without the n, the constant, as say, for each individual in the population during a small time period with length delta t, its rate of giving birth is lambda times delta t. And its rate of dying, its probability of dying, its probability of dying is approximately mu times delta t. And these are for single individuals. And if you consider the population as a whole, then the population increase by 1 unit will have a probability of n times lambda times delta t. So the idea is the larger the population, the more likely that you will see a growth in a small time period. That makes sense because more individuals, just more possibilities for the process to grow, right? It's like a compounding effect. If you have a bigger subscriber base, then it's likely for those subscribers to recommend to their friends, and you get more subscribers. Every YouTuber's wet dream. And by the way, Leo, not thank you, but congratulations to your 1K sub. Awesome. Keep it going, right? I see great potential for your channel. And here, also, on the flip side, let's say if you have a large subscriber base, it's also more likely for people to unsubscribe, right? So that's the death rate. Right, mu n equals n times mu. So birth and death process is actually an excellent model for YouTube channel growth. Okay. Anyway, I'm not sure if this is Malthusian, but this is a common model. Okay, fundamental importance in population dynamics. So individual. This means individual, independently. Each individual independently gives birth at a rate of lambda and a death rate of mu. So this is where the assumptions become difficult to verify, right? How do you verify, say, each individual independently gives birth or dies? Right? So this is where the assumptions become difficult to verify. So the validity of the model really is checked based on their predictability. Right. So what consequences do the model assumptions imply, and how do those consequences, theoretical consequences, compare to reality? Okay, so this is another way to assess model validity. You can't always reliably check the model assumptions, but you still need to make assumptions to make progress. And dies at rate mu. So how does PDE get into this business, right? Because so far everything is discrete. The state, I mean, not everything is discrete. The time is continuous, but the state is discrete. How does PDE model comes in handy here? Well, PDE model comes in handy due to what we call the generating function. So what we're really trying to study is PNT. This is a sequence. This is a sequence, P1, P2, P3, okay? These are sequence, although sequence numbers are time dependent, but this is a sequence. You can think of this as a sequence. PNT is a sequence. So for each sequence, if you fix T, okay, if you fix T, a sequence would have a what we call a generating function. There is a one-to-one correspondence between the sequence and a power series. Okay, let's try to review that idea. So the idea, recall, this is super important in combinatorics and discrete math. It's another reason not to neglect calculus if you're only interested in discrete math, is because there's this powerful tool in discrete mathematics called generating function. Okay, and really, generating function is such a broad topic that it encapsulates fields such as Fourier transform, Laplace transform. Okay, these are just fancier, more powerful generating functions. So here we're only dealing with generating function of the sequence. Generating function of a sequence. So the idea is there is a one-to-one correspondence between a sequence, say Pn, this is a sequence, and its corresponding power series. Remember here, let's say n is greater or equal to 0. So this series is Pn s to the n, where s is an auxiliary variable. Okay, s does not have any physical meaning. Okay, it's just a way to encode the sequence. There's a one-to-one correspondence between a sequence and a series. Okay, and for the moment we do not care about the convergence of the series. So this is a power series. Generating function of a sequence, the idea of that is the one-to-one correspondence between a sequence and a power series. If you know the power series, you know the sequence, because you can just extract the coefficient of the nth power and you get the sequence. And of course, if you have the sequence, you can define the power series. And we call the power series a formal power series because we ignore convergence issue. Okay, so there's that. Okay, so here we have the this idea. Let's take a look at an example. For example, if you just have a constant sequence, say if you just Pn is constant 1, is a constant 1, then it would correspond to the geometric series. And from 0 to infinity, s to the n, this will be 1 over s, okay, assuming convergence. Okay, so next we have, for example, another example. Let's say Pn equals 1 over n factorial. Let's say Pn is 1 over n factorial. Then here, the sequence would be the exponential function, Sn over n factorial, and this way you get e to the s. Okay, these are examples. Generating function relates in a one-to-one manner between a sequence and a power series. So based on this idea, we can define a probability generating function. So for a given non-negative random variable, non-negative integer value random variable, say x, right? We have the PMF. We have the PMF. It is described with PMF Pn. Okay, PMF Pn, which is defined as the probability of big X equals little n. We define its probability generating function as follows. Define PGF of x as follows. Probability generating function, aka PGF, probability generating function, which is simply the generating function for the sequence Pn, right? Sequence here, n is equals 0, 1, and 2, and so on. Okay, guys, I'll come back to chat in a second. I really wanted to finish defining this and deriving the PDE satisfied by the PGF. So that's the whole point. The PGF satisfy a PDE, and that is easier to handle than a infinite system of coupled ODEs. Here, the forward equation, the Kolmogorov's forward equation, is a system. This is a system of infinitely many ODEs that are coupled. So this should be a very difficult problem in general. Indeed, forward equations are difficult to solve in general. Okay, so Kolmogorov. Forward equation. Also, there's Kolmogorov backward equation, but that's beyond what we're discussing here. So the system of ODE is infinite. The idea is we can encode all of this. We can encode all of this using a PDE. Okay, so we have 10 minutes left. I'm not sure if I can finish the derivation, but we'll do so as fast as possible, and I'll answer a few chat questions. Okay, so there you go. The definition as the following. So let's call it G of S. So G of S, this is defined as the sum of Pn, Sn, n from 0 to infinity, namely the sum of probability of big X equals n, s to the n from 0 to infinity. And there's a probabilistic way to write this because that's just the expectation of s to the big X. So all same are equivalent definition. The probability generating function is defined as such. Okay, so now let's come back to the random variable x of t. X of t, well, is a random variable that depends on t. So its probability generating function would have its own auxiliary variable s. S does not have physical meaning. Okay, S does not have physical meaning, but it is a continuous variable, like in a power series. So for, let's say, BD process, for the birth and death process x of t, right, its PGF is defined as follows, which is G of S and T. Okay, is defined as the probability of xt equals n times s to the n from 0 to infinity. Okay, or the expected value of s to the xt. Same thing. This is its PGF. So to facilitate solving the Kolmogorov's forward equation, we can actually derive a PDE for G. Okay, G satisfies a PDE. So this is where the punchline of the story. Satisfy a PDE. A first order PDE, in fact. And we'll see how that's done. Okay, hopefully I can finish up this part of the derivation in a second. Okay, so I have 5 minutes left. Okay, based on the Kolmogorov forward equation. So start with forward equation. Start with forward equation. Which is, let's use physicist notation, Pn dot, which means time derivative. Pn dot equals lambda m minus 1. Okay, just the specialization of this. Okay, lambda m minus 1, as you can see, for linear birth and death process, these are the special formulas. Okay, so it will be lambda times m minus 1 times pn minus 1 plus mu times m plus 1 pn plus 1 here. This is yeah, these are terms, and then minus lambda plus mu quantity times n pn. So this is the forward equation. Okay, so now let's multiply both sides by s to the n and sum. So we wanted to cook up a equation for big G. Multiply by s to the n sum over n greater or equal to 1 and see what that gives us. So the left hand side, let me write down the equation in full. So what I mean is the sum of pn dot s to the n from 0 to infinity, and then equals, okay, lambda can be taken out. This is the series. It goes to yeah, the series, I mean, we're not going to investigate convergence. In fact, we just treat it as a former series. Okay, convergence is not the primary issue here. We really care about the coefficient expansion of the series, not the value of the series. The value of the series does not concern us very much. So here, oh, actually here, this is n greater or equal to 1. We also need the equation for n equals 0. So for n equals 0, yeah, this is a separate equation, p0 dot. P0 dot. Okay, so this is p0 dot. P0 dot. It would be mu1 times p1. Mu1 times p1 would be just be mu1 times p1. Just be mu times p1. Okay, mu1 equals mu. And lambda naught is 0, so there's no this term here. Okay, so this is p0 dot. P0 dot. Okay, so what I was saying, for the first equation, you should start from sum from n from 1 to infinity. Otherwise, it doesn't make sense. We can take care of the zeros order term later. Okay, so sorry, I'm just gonna put the dot here. So these are the forward equations for the. This is the linear process. Okay. If I want to emphasize, this is for Mouse's or linear birth and death process. Not always, okay? Not every birth and death process have a G that satisfies the PDE, but for linear PDE process, aka Mouse's process, it satisfies the PDE. Okay, you sum over n equals 1. My God, I only have 2 minutes. Okay, because I gotta go soon. Okay, maybe I should just write down the answer and leave that as an exercise. Sorry guys, we will definitely come back to this. Okay, so basically G satisfy PDE, that's the result. Okay, if you do this, and you can get dg over dt equals s minus 1 times lambda s minus mu dg over ds. So even though seemingly the problem itself, the birth and death process, is not modeled by a partial differential equation physically, okay, solving its fundamental equations requires or can be achieved by converting it into a PDE problem. Okay, and this is actually what physicists prefers. So physicists, when it comes to studying stochastic differential equations, like to convert this into a PDE, whereas financial mathematicians like to study SDEs as using probabilistic tools like martingales. Yes, it is similar to Taylor series, but it's because power series really are Taylor series. Okay, provided converged, and power series and Taylor series are the same thing. So sorry guys, I know this is rather unsatisfying, but we will make a follow-up stream next week to finish up this derivation and see how the equations are actually solved, like this one, like the traffic flow equation as well as the birth and death process one. So these are, I think, great motivating examples. Okay. Once again, by the way, what is this? This is linear first order, okay, not quasi-linear. So this is linear first order, and the solution behavior between linear and quasi-linear is great. Okay, even though there's only one suffix of difference, linear and quasi-linear differential equations behave totally differently. Okay, so that will be for today's stream. Thank you very much guys for watching it, and we'll see you